Hello. We are back and we'll be, this is our day 9. So we'll be studying some concepts. We have studied GD, gradient descent. We have studied SGD, and now we have a new, concept. And all these GD, SGDs, well, they were just a simple, starting point in terms of AI and architecture of these things. So we now have to get more complex. As for in Rust, I think, from the past 2 weeks, I was only focusing on most of the Rust. So I think I'm a bit better in Rust compared to day 8 because of the long time has been passed between them. Uh, so let's get started with the, concepts. And before that, let's set up our environment, which is, our Rust and sort of terminal. Where were we? Project learn, then Rust, then day 9. 9 day. All right. 9 day. And it's empty. All right. So it says good. This is the first day where numerical linear algebra directly controls the system behavior. And we will not let this become blind implementation. So we proceed to concept first, which will be, our concept. And then we code it, and then we report the benchmarks or the numbers. So concept one is, what does condition numbers actually mean? All right. So what does condition number actually means? So we are not defining it formally first. We derive its effects. You are minimizing this, formula to a gradient and then Hyesen's. So these Hyesen's is something, we've studied, I guess, in day 8, and gradient descent, in day 7, I guess, isn't it? This was y predicted, this was actual y. We subtracted them to calculate the error. Then we multiplied it with x transpose and calculated its mean by dividing it over n. And this was the same, just a bit different. So it looks different because there's, first of all, 1 over 2n, not just n. And second of all, we are penalizing the error more. So it's like squared. So what can I infer from this? What does it want me to infer? So it says, first of all, you are minimizing this formula, which is L over W equals to, what was W? Okay. L over W is equals to 1 over 2n, like divide by 2n. Instead of just n, we are, I don't know, we are dividing by 1 over 2. I don't know why are we hopping that, but we are hopping it. And why was the n present? Because we want to take the mean, but now there is 2n, so it doesn't make much of sense. And then there is this x that we predicted through multiplying, x with our weight that we calculated randomly, and we are subtracting it by y. So this is what we get or call as an error, and we are penalizing it by squaring it. That's what I get, or that's what I infer from this equation after a long time. Gradient, well, we've known this formula for a long time, actually 3 days. And Hyesen's, so it's like 1 over n x transpose multiplies by x. And what it does is, I think, takes over the mean of x multiplied matrix or multiplied by its transpose of it, and we are taking the mean of it by dividing it by n. Now it says key insights. So what should we insight upon is, gradient descent gets updated, like w for t plus 1 is equals to w t minus n. That is, if it was upright triangle, I would have said something like delta, but since it's upside down, I don't know. And then L. Now convergence depends on the geometry of H. H is Hyesen's, so it says convergence, that our data converges together, is, well, dependent on the geometry of H. We don't know how, but we'll get to know it. That's why we are learning concepts now. So what geometry? So it says diagonalize something like h equals to qa and qt. So is it qa or it's like q and upside down v? What is it? Let me just zoom it a bit. Yeah. So it is not a. Ah. So this is sort of a symbol. Uh, that means we are, calculating a diagonal for the whole lambda 1, lambda 2 to lambda d, whatever the lambda is. And we are multiplying it with q and the transpose of q to get Hissens. All right. Now it says think carefully that each eigen direction updates. So eigenvalues updates like what? T plus 1 and this wt minus n lambda wt. So we take w common, or we do this. We take wt common, isn't it? And we get left with 1 minus n lambda I in bracket. And then that t from here comes up over here. So it becomes minus t, so it becomes w equals to 1 minus n lambda I. So what can we infer from this? Well, I don't know how to infer from that, but all right. So speed depends on lambda I. All right. So it's telling me the inferences that we can take from these equations is like speed depends upon lambda I. And now let's zoom out a bit because it's too much. Now it says we have a problem that if we have a large eigenvalues like very big and small eigenvalues is very small, then one direction moves very fast and one direction moves very slow. So this creates a zigzag oscillation where we don't, converge properly. So this is our problem for now. Now the condition numbers. So this was kappa, isn't it? K over the h, which was Hissens. All right, not Huygens, but Hissens. So K is like kappa over Hissens value is like lambda max upon lambda min. So we have seen this. We've seen this already. All right. Now interpretation is so they're like not definition. This is just interpretation that kappa if equals to 1, which means that lambda of max is not or is very similar to lambda of min, like is not going very far away from the lambda of min. So minimum and maximum lambda are very close. So that's why we are getting near of 1. If it is 10 to 100, it means we have a mild elongations, which means lambda max is 10 to 100 times larger than lambda min. That's what we can infer from this. And if it's 1000 plus, it means that uh, it is extremely stretched and it is now very slow. As for perfect sphere, that's what we want. It means that it is very fast convergence. And 10 to 100 means mild elongations, and 1000 plus means extremely stretched, which is slow. So a data set causes bad conditioning. You will create something like X, which will be similar, or sorry, near equal to N from 0 to 1, in decimals, 0.001 or whatever. I don't think that's what it means, but I'm assuming. X2 will be similar, equal thousands multiplied by the number that we get from here, this N and 0 to 1. So the variance 1 times is 1, whereas variance 2 times is nearly a million. Oh, how did we get to this point? Like we were multiplying 1000. Yeah, that's understood. But How did we, added three more zeros to it? I think we are squaring the number, so we are squaring this, somewhere. Is this because of it? I don't know, but sort of because of square, it can become, million. Now we are seeing the effect on h, which is Hessen's value, is equals to x transpose by x multiplied by x. All right, so eigenvalues roughly scales with feature variance. So lambda max is greater than lambda min. So like 100 to 1000 times greater than, a large greater than lambda min, which means that kappa is now greater than 1, like nearly 100 or 1000. Right. So kappa will be greater than 1. How did we infer this? Well, because of this one, this formula. All right. Now, why standardization fixes it? So you transform the x to, x minus mean over standard. Now the variance is, you know, equal to 1 or very equal to 1. It's coming towards 1 for all features. So action values become similar. So kappa is small. Momentum, well, we are taking the intuition only. So for standard GD, we had this formula where we were, W minus equals to like assigning it again. But let's do it properly like an algebra, not like a C operation. You know. So over here, we are saying that W is becoming or getting assigned the value of W minus LR multiplied by grad, which is, gradient. Uh, Now the momentum is something like V is equals to beta multiplied by V again, and we are adding grad to it. And instead of just multiplying with the W, the LR with grad, which is gradient, we are now multiplying it with the V. Okay, so this is our momentum, and we are using that momentum for W. Now what changes? So instead of reacting only to the current gradient, you accumulate directional consistency. So this damps the oscillation, accelerates flat directions. A critical mistake student makes is that this is wrong, where we are doing something like, oh, we are adding LR. We shouldn't be doing this. And directly, assigning the W as a value of W minus B. We shouldn't do this. What is wrong over here, first of all? What can get wrong? Yeah, this. So LR multiplied by grad, and then we are not doing that. We are not multiplying grad with LR. Like let's try writing it down. So what I will do to solve this equation is like W is equals to W minus LR. This is the equation, and instead of V, what I'm going to write is inside a bracket I'll write the whole value of V. So it's beta, oh, beta, and then we are multiplying it with V, then we have addition, and then we are adding grad to it. So to open this, what we have to do is, we have to multiply LR with first of all beta multiplied with V, and then we have to do the LR multiplied with grad. Then I think we can open this up. So it will become W minus LR, and we are multiplying it with beta, and we are multiplying it by V, and then plus minus, from here minus, you have plus, it becomes minus, so it will become minus LR and multiplied with grad. I think this is a basic algebra, nothing too fancy over here, but still let us see if we did any mistake. So minus LR was there, so we multiplied LR, so it became minus. Beta spelling is mistaken, so beta. So we could have written something like this, but we cannot write it like this. Why not? We got the point. Because, we are not multiplying LR just with the grad. We are also multiplying that LR with beta into V. So until and unless we do this, LR over here, we can't just subtract it with V. Like right now, if I substitute V as this, but then it will not be a momentum. So yeah, but if we wanted to, really, we could just do it like this. Like we have V, let's make a variable X and then substitute X as LR multiplied by V. That would suffice also. Then we can do W minus X if we wanted to, make this equation less scary. But this is not scary at all. So we would not do this mistake because that would be, breaking the rules of algebra. Because if LR is getting multiplied by V, it should get multiplied with the whole V, not just the grad part. All right. We are multiplying only the grad part, which is our mistake. We should also multiply it with beta multiplied by V. We would also multiply LR like this. And that will make this thing work. So that's why this is broken or wrong, and this is working. So this is correct. Let's erase our sort of intuition from here. Let's move on. So it says, before you code, you must pass this. All right. So section A says, well, we have some questions, nearly 3 questions. So let's try answering them. So first one says something like, why does large feature scale difference increases the X? So why does large feature scale difference increases the K? Because gradient becomes 0, because eigen value of H spreads apart, because learning rate increases, because noise increases. So I think before attempting this, we should go back again, because this is a new concept for us. So let's go back again and try reading it. Just reading it. So concept 1, what does condition number actually means? We are not defining it formally first. We derive its effect. So you're minimizing the L equals to 1 over 2n, and then in modulus, I guess we have xw minus y. We are squaring it, so to penalize the error. Then we have a gradient formula which is similar. I'll call it delta for now, but I don't know what this is. But delta L is equals to 1 over n xt, which is transpose of x matrix, and then multiply that with xw minus y. Now Hisson's formula looked something like this: h equals to 1 over n x transpose and x. Sometimes we divide it by n, sometimes we don't. Like below this, we didn't sort of divide it with n, but over here we are. Now key insights. So gradient descent update. So key insights is that gradient descent updates is like wt plus 1 is equals to wt minus n and lambda l. Why could we do this? Well, then I would love to substitute this over here, and would get cancelled. We'd left with x transpose and x multiplied with w and y. Then we would do something with x and x transpose matrix. We would do something with y. We would be left with w, and somehow we might have taken it as new w, so it became t plus 1. I don't know how this equation came to life. I'd love to know that, but not right now because we have lots on our hand. So convergence depends on geometry of H. Convergence depends on geometry of H, and we don't know what the geometry is. It says what geometry? So diagonal I is like H is equals to Q and then upside down V, then Q, T. And I am assuming Q are the matrices, isn't it? That's why we have a transpose of it. Where this upside down V is equals to, diagonal of all these lambda 1, lambda 2, lambda till lambda D. Now it says think carefully that each agent direction updates like this. Yeah, exactly this. So L can be also written as, so I've written L or that delta L as, yeah, we have written delta L as lambda I Wi. Now think carefully that each agent direction updates like this, with this formula. So speed depends on lambda I, which is this element over here. So speed depends on it. Now the problem was that if largest eigenvalue, then everything would be very big. Smallest eigenvalue, very small. One direction moves very fast, one direction moves very slow. Now that creates a zigzag or oscillation. So condition numbers. We have this condition number where kappa is equals to lambda max upon lambda min. We know that. Interpretation is like if it is very similar to or very close to -1, then it would mean that we have a perfect sphere, which means a fast convergence. If it is between 10 to 100, it has mild elongation, which means not very fast. And if it goes beyond 1000, it is extremely stretched, which means very slow or slow. And why your data set causes bad conditioning? You will create something like x1 is, n 0 to 1, and x2 is 1000 multiplied by n 0 to 1. So the variance for the first one is 1. Variance of x2 is, a million times. It says effects on h. So we have h, which is equals to x transpose multiplied by x. Why aren't we dividing it by n? I don't know. Like earlier we did at the top. Yeah, over here we did multiply it with 1 over n, which means, dividing it by n. But below over here, like we are not. So I am a bit confused right now, but this is AI. This is how it can help. And if I, suddenly ask this question about it, it will go into some rabbit hole. So I don't want to go into a rabbit hole right now. So these are some questions for another day. But the eigenvalue says roughly scales with feature variance. So lambda max is greater than lambda min, which implies that kappa will be greater than 1, like very greater than 1. Why standardization fixes it? So we transform the x to, x minus mean upon standard. So standardization sort of fixes this because we divide it by x minus x mean. Now variance is 1 for all features. Not like this, but like this. And so eigen value becomes very similar, which is, small for everyone, not 1000 times larger. Now momentum. So intuition only, that standard GD looks something like this. Momentum is, V, which is beta multiplied by V multiplied by itself. And then we are adding grad to it. Then we have W, which is equals to W minus LR multiplied by V instead of gradient, grad. So what changes? Instead of reacting only to the current gradient, you accumulate directional consistency. This is like damps the oscillation, accelerates the flat direction. A critical mistake student makes is, the algebra mistake. It says before your code, answer this. Why does large feature scale difference increases the K? So if there are large feature scale difference increases the K because gradient becomes zero because action of H spreads apart. I think this is it because learning rate is increases because noise increases. Well, I think because of P. Now two. So what is the second question? So second question is if K is very large, GD will be. So K means kappa is very large. So lambda max must be very larger than lambda min, which means it will be very slow, isn't it? But we are not talking about speed. We are talking about GD, gradient descent. So it will converge faster? Never. Will it oscillate and converge slowly? Well, I think so. As for diverge, always, I don't think that it can, like, it might happen, but not in the case. Like, very large means what? 1,000 times? Then we have seen that it can be slow, but it never said that it will never converge. So, extremely stretched, but it is slow, but it might work out. So, I don't think it will diverge. But it might if it is very very large, like not just 1,000 but million or billion times larger, then it might start diverging, and that's not our goal right now. Third is standardization reduces kappa because it reduces the data set. No, it equalizes the feature variance, it removes the noise, it reduces the learning set. What we did in standardization was x minus mean, and then we divided with standard std. So does it reduce the data set? Or it equalizes the variance? Well, I think it equalizes the feature variance. Well, we are not, grasping it very properly, but still, there are some bell ringings in our head for now. Now there's section B, section C, section D, section E. Let's read what are we going to do. So section B will be all about code prediction. So we'll assume something like X is N01, X2, which is this question, like which is larger. Oh, so this is our question also. So I'll think this as fourth question. And which is larger? So obviously we got, the x2 will be larger because of this 1,000, which will be squared, so it will become a million. So lambda 2 will be larger. Explain why and not just answer. Now explaining why is a bit of a headache because we still can't grasp the situation here. But let's try saying something like it will become million times because of the 1,000 squared. And how that happens, we'll need some more help. FIGU, So I tried explaining that it doesn't work. We don't know right now, but section C. So I'll treat it as question 5. It says explain in your own word why does GD zigzag in ill-conditioned problems? Yeah, I've seen this explanation somewhere. Like it zigzags. Why? Data does not converge properly. So, well, it doesn't converge P-E-R-G-E, converge properly, causing it be slow and go zag. As for a better explanation, we might have, it'll say this is incorrect and will give us some better example too. Yeah, we should just sit tight with this lecture or whatever this is, demonstration, and we'll learn something new today. That's my gut feeling. So you compute something like h, which is Hysen's, which is x transpose multiplied by x, and then average it out by dividing it by n. Then egg value, which is eigenvalue, will become something like np, which is numpy's linear algebra, linalg, so algebra, linear algebra, dot egg value, which is h. So we are passing it h. A question: why is dividing by n not affecting the k? So dividing by n does not affect the kappa. Well, how could it? Oh, damn. I need lambda. So what is lambda actually? Like kappa is lambda max over lambda min, but what is lambda? And how is it proportional to n? Should it get affected? Should it not? I don't have much of an idea right now. It says why dividing by n not affects k. I think we are dividing by n to get mean and converge the value LUE, but I don't see a relation of lambda, which is PRO proportional to n, but it is proportional to kappa, isn't it? So kappa is directly proportional to lambda max, inversely proportional to lambda min, but I don't see some proportionality sign saying that lambda is directly or inversely proportional to n. Like I don't see any of that, so I don't know how it should work. Seventh, which is section E, mini coding task, manual thinking. Write a pseudo code which standardize X. Constraint is no sklearn, must handle multi-thread matrix, must avoid division by 0. Oh, how should I do that? I don't know. Just make me familiarize with the concept first. Just make is with the concept first, isn't it? Now it says stop. Stop what? Don't start coding full task yet. Answer all the sections. I will validate your mental model first. If it is wrong, your entire day 9 result will be gone. Oh shit. You attempted everything. Now we tighten your understanding. You have a partial correctness because, yeah, I have a partial knowledge, not a full knowledge, and critical gaps. Well, that's expected. So I answered B, which is correct. Eigen values spread apart, so K increases, isn't it? Eigenvalue, lambda, eigenvalue, same, isn't it? And the second answer was slow and oscillatory convergence. So it asked me something like, if K is very large, GD will what? Yeah, so yeah, it will obviously slowly try converging it. So slow and oscillatory convergence, which means zigzag convergence, isn't it? Oh, so in zigzag question, I should have answered like uh, kappa will be very large, uh, then convergence will be slow, or slow and oscillatory, which is zigzag convergence. I should have answered something like that. Uh, and question 3 was answered also correctly, which is equalizing variance compresses eigenvalues spread. So this is also correct. What was the question 3? Question 3 was something like standardization reduces the kappa because. So question 3 was standardization reduces the kappa because the equalizes feature variance. Yeah. X minus mean by standard STD. So we were sort of subtracting the mean value from X uh, and we were dividing it by STD, whatever the value of standardization is. Uh, so I did not have a full grasp or idea, but still answered it. So let's move on with that. Section B, where eigenvalue reasoning, you are shaky here. I am shaky everywhere right now. You said lambda 2 becomes a million times because x squared, but unsure why. Let's make this precise. So core rule is something like h, which is Hessen's value, is equals to 1 over n x transpose x. All right. Now it says look at one feature, which is h for I. Rows and columns. What is II? Like, what should I expect from II? Is it rows and columns together? Let it go. So we have 1 over n for mean, and we are summing it. Summing what? Summing x over I, like x1 squared, x2 squared, x3 squared, something like that. Right? We are summing it all, and we are dividing it by n. So how many numbers of x were there? 1, 2, 3 in my case. So we'll divide it by 3. So that's equals to variance, roughly. All right. Now we see that x1 is, from n from 0 to 1. So x will be first of all 0, then it will be 1. And so we are summing 2. So n is, 2. All right. So it says E. Now what is E? No idea. But E, I think it has written this summation as E. That's what I can assume right now because we have x1 squared, which is for 1. Instead of I, we have 1 squared, which is roughly equal to 1. And then x2, we are multiplying 1000 with it. And then we are saying the same thing for n from 0 to 1. And E, which is, I guess summation, is again for x2 now instead. And we are squaring it. So we are also squaring the 1000. Oh, so my guess was actually correct. All right. But it was not from the gradient descent formula, but it was from this h, calculating the h essence values formula. So yeah, I think my assumption of how we could get a million was correct. So therefore, the lambda 1, which is eigenvalue 1, is 1. Lambda 2 is million times because of this 1000. So my intuition was correct, but you lack the reasoning link. Eigenvalue is similar to variance along directions. How that is equated, we don't know yet. But we now know that eigenvalue is very similar to variance along the directions. Now section C, zigzag's explanation. It is very weak. Yeah, it is. So I said something like doesn't converge properly, slow zigzag, and all that. This is description, not mechanism. Correct explanation would be you must internalize this. So gradient descent updates per direction. So Wi for t plus 1. Oh, we are squaring it now. All right. So Wi and squaring it by t plus 1. Not squaring it, but to the power of t plus 1. So whatever the t is. If it's 1, we are squaring the Wi. If it is 2, well, we are cubing it. And so on. Now that is equals to 1 minus n. lambda I multiplied by wit. So I must internalize this first of all. Well, I can't, but I know where it is coming from. We had an equation something like wit plus 1 and then wi minus n lambda I wit. Exactly that equation, just w has been taken as common, and I was sending that wt over here, and the power of t, was getting subtracted by my equation, and like we were left with just w to the power of 1, which is w itself. So that's why I said earlier w equals to 1 minus n lambda I. But I don't know how that's work. Like, do we even need that equation? Or do we need it in this sort of formalization? So it says now the large lambda will be big step, which is like overshoot, whereas the small lambda will be a tiny step, which will be a slow progress. So if it is very large, we take a big step, which will just overshoot it. If we take a small step, which is very tiny step, it will make a slow progress. Now the result says that one direction overshoots, which is oscillation, other direction crawls, which is now slow. So combined with a zigzag, combined gives us a zigzag trajectory. So one direction overshoots. Oh, if I recall properly, I have well heard of this concept somewhere in day 7 or day 8, where we were talking about L graphs, isn't it? So on the same learning rate, we were playing with learning rates. We were making learning rates differ. So on the same learning rate, if we have something like L graph, so on the slope, it will shoot very fast. So it will just overshoot. But on a plane, it'll take very tiny steps. So that will be a slow progress. Or am I speaking vice versa? In slope, it might be slow and take a slow progress, or in a plane it might take a big step and overshoot, whatever this was. But we might have studied this concept somewhere in L graph on day 7 when we were playing with learning rate. We were making it very large and very small, and we have heard something like our data set might burst if we made it not in some equation that we should have satisfied, uh, isn't it? Because of our features, which were only 3, isn't it? That's why thing didn't burst out. But I still don't know what the burst out means. So let's see. So it's giving us a different concept now, like the same concept, just more details. So it says one direction overshoots, which means oscillation, whereas one direction crawls, which is slow. Combined, we get a zigzag trajectory. And if I were to guess, I would guess something like on plane it would overshoot and will then oscillate, whereas in slow it will crawl and be slow. So L, or a slanted L, something like backwards L, or something, if I can say backslash, or this graph, not this, slanted L, this sort of graph. All right. Now section D was dividing by N, important gap. You said, what was section D? Why is dividing by N not affecting the kappa? So I don't see much of a proportion between N and a lambda. So therefore I don't see any proportion between N and kappa. That's what I said. So you said mean not relate to lambda. That is incorrect reasoning. Well, I guessed so. So correct reasoning would be something like h, which is Hessen's value. We have xtx over n. If we remove the divide by n, we get Hessen, I guess, a temporary Hessen values. I don't know what this apostrophe means or what it should mean, but we have now without n, we have xtx, and we are multiplying the n with this Hessian h. So we removed the n from here. So eigenvalue becomes something like lambda I will become n lambda I. Now compute k with that. So it will get cancelled now. So if we have n on numerator and denominator, the n will get cancelled. So it does not affect k. So how should I say that in a statement? Now compute k. So our lambda became n lambda. So we are multiplying with n lambda max, n lambda min. We get this form, and then well, n gets cancelled and we get a normal k. So inside, scaling entire matrix does not change the condition number. So I think we could say something like k, since it's a ratio between lambda max and lambda min, the n will not change it because n might be common and might just get cancelled in the ratio. I think that would have been better than just saying I don't see a proportion. All right. But we didn't see that proportion. I did. Section E. So you say, well, I skipped this. Not acceptable. You must be able to write this manually. But I don't know what the standardize meant. So standardize, we have a mean where we are computing mean per column of x. So for each column of x, which is, if features are 3, we have 3 columns of x. Standardization, so compute standard per column x. And now I don't know what that means, isn't it? What does the standard means for per column of like matrix x? And it says avoid division by 0. So standard of standard equals to 0 will become 1. X scaled is equals to x minus mean upon standard and return the x scaled. Critical detail you must understand, mean, which is shape D. Mean is of shape D dash. What is that? D dash D1, I don't know. And standard shape is D dash again. So both of them have the same shape because, well, I don't see much of a difference between them except for just the name standard per and mean per. And what it does, if well, to avoid division by 0, where are we dividing? Over here. So we don't want a standard value to be 0. So as soon as standard value becomes equals to 0, why do we have to pass that in standard again? But we are doing that anyways, and we are assigning that a value of 1 explicitly. So it will never get a value of 0 over here in this fraction. And then we can calculate this x scaled and return that x scaled. So mean and standard have the shape, well, very similar or same, and broadcasting applies to row wise. Broadcasting applies row wise. So row is something like this, horizontal, columns vertical. So broadcasting applies row wise. And now I don't know what the broadcasting means. So should I write this code somewhere? Well, let's not copy it. Let's not copy it. Let's not make the mistake of copying and pasting. So let's open up the Colab, a new window, and we will do this. All right. So we have to define a standardize. Let's first of all go to that question, which was section E, mini code task, manual thinking. Write a pseudo code for standardize X, constraint, no scalar, must handle. So let's copy this instructions and let's add a text. Let's paste this text. Let's say this is good. Now let's start writing standardize X. I think we can stand Don't make spelling mistakes. Standard dice. We are passing x. Good. And we want to define it. So let's add a define. Standard dice x. We have mean value, which is, taking the mean from the, well, x, large X, which is signifying that it's a matrix, not anything else. Standard, well, we were having a long procedural name for that. Here we just say we have standard getting by column but X. Then we were implying not division by 0. So what we did was we took the standard and we passed a standard which was equal to 0, and we explicitly made it equal to or assign it a value of 1. Now, why we did have to, say standard inside that we have standard? I don't know. We could have just said if standard is equal to 0, we could have made that equal to 1 just using a if statement. But doing this, it doesn't make much of a sense to me. Well, doesn't mean it's stupid, just I don't understand it. Now the formula, which was x, scale, SCALED, is equals to x, minus mean, and then we were dividing it by standard. So we'll say / std standard, and then we said return RETURN x scaled. Why am I not getting any auto suggestions? I think because it's not connected right. So let's try running it. It will not run because we are not calling the standardize on anything right now, but our computer will get connected. So yeah. Now let's match this with our program. Sorry, not our program, but GPT's program. It must be same because it was a small function. Standardize. Let's see. Over here. Compute mean per column. And let's, change this also. So we'll say compute mean, and then we'll say per column. Why are we getting yellow? That's mean for you. Why is it yellow? Undefined variable. Oh. Oh, shit. So is it like compute mean per column? Is it some sort of function that we have not yet defined? Damn. Exactly. Like, why would we just pass x just in a variable? Yeah, sorry. I'm a bit slow. I'm grasping stuff. Compute standard per column. COLUMN. So we have to define two functions: compute standard per column and compute mean per column. And then, well, we would not get any yellow signs or signals. This is correct, absolutely correct. So not division by 0, it's not division, but avoid division by 0. Avoid division by 0. That's clear now. X scaled is x mean divided by standard, and we did not use the brackets. Let's use the bracket so that we do the subtraction first and then division, and then we are just returning x scaled. Now critical detail was we missed, you must understand, not that we missed, but the mean shape D. Well, yeah, it is taking the same matrix, so obviously both have the same shape. Broadcasting applies row wise. I don't get that again. what does broadcasting means in itself, and then what does it mean when it applies both ways. Now it says retest, you must answer again, you are not moving forward yet. If one eigenvalue is 1,000 times larger than another, what happens if learning rate uh, is tuned for small eigenvalues? Oh shit, we'll get a zigzag. Well, if learning rate is tuned for small eigenvalue and we suddenly get a large eigenvalue, what will happen is small eigenvalue would have moved well normally if we have tuned it according to it. As for a larger eigenvalue, well, it'll just diverge in large direction. Because kappa is, let's say, now 1,000 times. I would just say B, because that makes much more sense. Like divergence will occur. It will not converge like zigzag or anything like that. It will now diverge because, well, learning rate was tuned for small eigenvalue, and now we are suddenly giving it a very large eigenvalue, which is like 1,000 times larger. Well, yeah. So it will diverge in large direction. That's what I can say it is doing. As for two, mechanism check. So why does momentum help in ill-conditioned problem? Momentum was V, which is equals to beta multiplied by V minus a grad, isn't it? Well, it cancels the gradient or reduces the learning rate or accumulates the consistent direction and damps the oscillation. I think it has something to do with gradient because we are subtracting grad from it, which is gradient. So I'll say B again. Should I give it a formula? Well, I know the formula, like V is equals to beta or alpha, like whatever, a variable, and that's multiplied by V, which is momentum. And we are subtracting the subtracting what? Subtracting the grad from it, which is gradient. Now three, which says is if lambda max is 1,000, well, a million times lambda min, what is K? Well, K is equals to million, like 10 to the power 6. Can we say like that? Let's write it down. All right. 10, 1, 2, 3, 1, 2, 3. All right. What does it imply about convergence? Very slow, uh, very slow, not slow, but slow. Either it might go zigzag, it depends on learning rate. It might go zigzag or diverge based on learning rate. Rate, RATE. All right. Let's write something like convergence. UNVERGENCE. We are saying this about convergence. Fourth, code prediction. So if you standardize features correctly, what happens to the diagonals of H roughly? Very large values, close to 1, close to 0, well, very close to 0. That's why we are doing it. That's why we are standardizing it so that it doesn't go very far. All right. Question 5 is we are getting to, well, I just wrote it like over here. Requirement, use NumPy. Oh, damn. Where? Where should I use NumPy? Handle multiple features, avoid division by 0. Well, we avoided division by 0. and handle multiple features. Like, yeah, if there are three features, then we have, well, to grab from three columns. And how to grab from a column of a matrix? How to grab a column from a matrix? Use NumPy. Well, to use NumPy, first of all, so this is our, let's say, second implementation. So let's write it down again. Where's the text? Let's write it down properly. Question 5. And let's try coding it. So instead of defining, first of all, we'll say import NumPy as NP. Then we'll try defining the standardize. Standardize. Is there spelling mistake? Yeah, not SE but ZE. That's English for you. But standardize X. Standardize. Yeah. Then we have to calculate a mean somehow. We are passing it to a function mean sort of per COL column, not cool. Mean per column of X, and then we should get what? We have to define this mean per column, and then we should have standard, which is like standard per column of X exactly. And then, oh, it did avoid 0. Not properly, but here we are. Well, it just copied and pasted my code from here to here, sort of. And then we are calculating what? We are calculating the X scaled, SCALET, which is equal. Well, it is giving the formula from my earlier code. It's exactly the same. But do we have to use NumPy? Where? So I think in the mean per column and standard per column, we have to use NumPy. How do we do that? I have no idea. So I'll say, oh, not define here, because if we define it over here, first of all, will not be, taken in this standardize, or it might because it's just Python. So mean per column. Now see, yeah. So that's how we use NumPy. Like I thought, where do we use NumPy? But now we see mean per column, and for X, for matrix X, and now we say NP. Uh, all these things. You have a column stack. What is that? Well, I need a solution for now. NP, how do we calculate the mean? Like, do we just say mean or we say column first? Column stack dot mean, and we just return it return. I think this is so wrong. This is so wrong. And it says handle multiple features, like multiple columns. That's what it says to handle. How do they handle that? Let's write something wrong. All right. Instead of writing nothing, let's even just define it and pass it. But let's write it. Standard per column. You have to calculate standard per column. So pass X, and well, not X, we can pass anything, but while using it, we must pass X. That's what it did. And what it does is it returns what? Returns 1. I don't know how to standardize it. How should we standardize it? Did we get any formulas? Well, we did, but I don't remember them. So standardize per column. I'll just say I tried my best. Well, not best, but still, I tried. Here is my wrong implementation. Once you pass, you start full Day9 implementation. Well, I will. So it says we need to correct multiple things. You are close, but there are still critical misunderstandings plus broken implementation. So section A is like evaluation. So question 1B correct, which is, large eigenvalue direction will diverge if LR is turned for lambda. Sorry, tuned for small lambda. And question B, which is incorrect, it should have been C, which is, accumulates the consistent direction and damps the oscillation. Let's see what the question 2 was. So why does momentum help, V in ill-conditioned problems? So I thought we were subtracting gradient from it. So it just cancels the gradient, but it accumulates the consistent direction. Yeah, I think I have read this statement somewhere while in the explanation of momentum. It is well in the direction or very consistent in the direction and damps the oscillation. How it does that? Well, not much of a fan right now, not much of an idea, but yeah, this was incorrect. Why your answer is wrong? Momentum does not cancel the gradient. It does something like this. Oh, now this is a different momentum formula. I think so. No, it's same. It's beta, and then we have a v, which is earlier v, vt minus 1, and then we are adding, not subtracting, but adding the gradient to it. So earlier we were also adding the gradient to it, but I sort of missed it. Where is the momentum? So we were adding grad, obviously. I made that mistake. Let's get back. Where were we? Yeah, somewhere here. Yeah, so this is our gradient descent, and this was our earlier v that we multiplied with beta and assigned that to a new v, which is vt. No. So it says if gradient keeps pointing the same way, they add up. If gradient flips, which is oscillate, they cancel partially. So this is how they dampen the oscillation, or this is how oscillation is reduced. Question 3 is partially correct. So you said something like kappa is 10 to the power 6, which is slow. Convergence is slow, not this, but convergence is slow, zigzag, and diverge depending on the LR. Good, but we should refine it. Something like divergence happens if LR is greater than 2 by lambda max. How did we get there? Oh shit. So yeah, that's why we should keep the LR in this limit. Like if it is less than or equal to this, lambda max in denominator, 2 in numerator, we are dividing that. So 2 over lambda max, if that is, the value that we are getting from there is less than LR, or LR is less than equal to that value, then we don't diverge. But if LR is greater than the value of 2 over lambda max, then divergence happens. So this is the case where divergence happens. So I don't just want to keep it in ChatGPT. I want to note it somewhere in my over here. This is important. Otherwise, it's very slow convergence and whatever, whatnot. All right. Question 4 was correct, which is after standardization, the diagonal of edge becomes near 1. Well, that was our concern, and we were solving that only. So we were trying to take it near 1. We did not want it to be 10, 200, or 1000 plus. We wanted it somewhere near 1. Now, section B, your implementation is wrong. I know because this is now how it works. So this computes a single scalar mean of entire matrix, not just per column. So you must do something with that. So it says to do that, we must do, axis equals to 0. That's how we implement it. But that will only, I think, take the first column if it will. Axis is like compute the arithmetic mean along specific axis. Oh shit. All right. We need mean per feature column wise. Exactly. Mistake 2, standard. We have not done anything. We have not implemented standard per column. So this completely breaks the scaling. You're not computing variance at all. How do we calculate variance? Mistake 3 is this line will crash. Why? You gave it to me. Standard scalar in your code. You can't index into scalar. All right. In our code, we have a wrong implementation. So yeah, this will crash. Mistake 4, broadcasting misunderstanding. So your current code looks something like this. Mean is scalar. All features get same shift. We need per column normalization. So correct implementation would look something like this. So let's see and tally with our own code. Oh, so we are passing. Oh shit. All right, let's see the real code. So instead of, defining these, well, we should define this first of all, you know, but we can directly write these also. Oh, this is great. For now, this is great. Mean per column, and we get a mean per column. Standard per column, we should get a return value of np dot standard, which will standardize it. We'll pass matrix X, and since we want column 1 by 1, so axis is 0. Right? I don't get many help. X is 0. So shape is somewhere around the same for everyone. So it was not anything D dash or anything. It was D comma. Right. So shape is D comma. Avoid division by 0. Now this will work because we can, well, index into our non-static standard, and everything works fine. Important mental model is if x dot shape is 1002, means we have two features. So the mean shape is 2 comma, standard shape is 2 comma. Yeah, so the shape depends on the features, number of features. Whereas this, what is this? 10,000. Yeah. So this 10,000, is it 10,000? Yeah, it is 10,000. So this is the number of rows that we should have, isn't it? So number of rows is 10,000. Number of columns is 2. Broadcasting mean. Acha, So this portion was broadcasting. All right. And then we were standardizing that broadcasting by saying broadcasting divided by standard. So means that for each row, subtract a mean 1, mean 2. So for each row, we have to subtract mean 1 and mean 2. Okay. So from the matrix X, we are taking per column first of all, mean per column, and then we are subtracting that. So it says retest. Again, we have again different test. Well, these tests and their explanations are making a greater mental model than we had before. So the explanation is working for now. So yeah, we'll do this. We are not irritated yet. But if we start going down a rabbit hole, we will have to escape it. If gradient oscillates like plus 10, minus 9, plus 11, minus 10, what happens to the velocity v? Keeps growing, cancels partially, and stabilizes, becomes zero instantly, explodes. Well, it should, we are introducing, velocity such that it can cancel partially and stabilize it. That's what it is there for. I think this will, try canceling it partially and trying to stabilize it. In which cases it should become zero instantly. I don't think. Should it explode? It is not very large, so it should not explode. Keeps growing. I don't know. B seems right to me. 2. Scaling effect. So before scaling, variance of x2 is greater than x1. After scaling, what happens to the xn value? Variance of x2 is greater than variance of x1, and after scaling, this scale still very different, becomes similar magnitude, becomes 0. Well, we are trying to make it very similar or near 1. The ratio should be near 1, so yes, it should become of similar magnitude. All right. 3. Critical insight. Why does large kappa forces small learning rate? Explain it one precise word. So now this sort of statement comes into play. Large K forces small, not mall, but small what? LR, because the, sorry, divergence will occur if LR is greater than 2 divided by lambda. Where's lambda? Just write it. Lambda max. One precise sentence. It is exactly one sentence. We are not explaining how lambda max, because we know that kappa is equals to lambda max upon lambda min. And since kappa is very large, it means that lambda max is figuratively, comparatively very larger than lambda min. That's why in the ratio we are getting kappa, which was a ratio of lambda max by min, large. It's not 1, which means lambda max and lambda min are not very similar to each other. It is that the case that lambda max is far greater than lambda min. In that case, we have a large K, and so when we divide 2 by lambda max, which is now large, and if that thing is greater than LR, it'll explode. So yeah, I think I answered it properly. 4th, code understanding. Given we have a mean and then NP mean X and then axis is 0, what is the shape of mean? Shape of mean is shape, spelling correct is, and then 3 comma. So this is our shape. Shape is this, exactly. So I think we can move on to question 5. If there is any mini code fix only this function. Well, I fixed it. And let me show it off to you by copying and pasting the whole lamp code. And then stop. Answer precisely. Once correct, you begin full implementation of data to kappa to GD to momentum and then benchmarks. So we have to do the same damn thing again, but with a new kappa, new JD, a momentum introduced, and then we'll benchmark it. Good for us. So we are learning some really cool things right now. It started hanging because my CPU usage is now, well, 90, near that. I don't like it, but I have to do with it. So good. This passes the conceptual gate. Only one refinement needed. So you answered almost correct. You said divergence occurs if LR is greater than 2. Oh, correct fact is, it is correct fact, but incomplete reasoning. Well, eh, it said one line, so I just made it one liner. So precise answer would be you must internalize this. Does it look like one sentence to me? Well, no, it does look like two sentences joined together with a comma. All right. Actually, it's just one sentence because one sentence means a full stop at the end. So the precise answer that you must or we must internalize is that large kappa forces the small learning rate because stability is controlled by lambda max. So large kappa is there, then that forces a small learning rate because stability is controlled by lambda max, while the convergence speed is controlled by lambda min, creating a trade-off. So this is the core optimization bottleneck. Let's again internalize this statement again. So large kappa forces the small learning rate means large kappa, learning rate small. Why? Because stability is controlled by lambda max and convergence speed is controlled by lambda min. Again. So large kappa, small learning rate, the stability is controlled by lambda max, speed is controlled by lambda min. So if we want a speed, we can try increasing the learning rate, which is, learning rate is like speed of learning per unit time. That's learning rate. In physics, everything is rate. Like uh, rate of change of distance is speed. Rate of change of displacement is velocity. So exactly the same way, rate of change of convergence speed is learning rate. So that is controlled by lambda min, whereas kappa is proportional to directly proportional to lambda max, which controls the stability. Oh, so I want again a new statement. With this, can I say something like, with this in mind, can I say something like whatever I say, but with this, what this is? With this statement in mind, can I say something like what? Something like A is directly proportional to uh, lambda max, and similarly LR is directly proportional to what? Learning rate lambda min. Lambda min. Can I say it like that? And next is your implementation. Well, my code is now correct because, well, GPT corrected me. So now we start our day 9 implementation. Before implementation, let's ask this question first of all. Then we'll see the implementation. And before implementation, let's add this text also. That the day 9 implementation starts here. Day 9 implementation. Oh, so many spelling mistakes. T-A-T-T-I-O-N. Implementation. And it's not day and bracket, it's day 9. I might have pressed. So no, that statement is not correct. And it will confuse your mental model. Well, it just did. So it says, let's fix it precisely. So you mean is lambda is directly proportional to lambda max. Sorry, kappa is directly proportional to lambda max. And learning rate is directly proportional to lambda min, because that's how I see it. Now this mixes the relationship incorrectly. Correct relationship would be something like that. You must separate them. So condition number is something like this, which is kappa is equals to lambda max upon lambda min. So kappa is a ratio. So kappa depends on both, not just lambda min. Learning rate constraint is like stability. So n, which is the learning rate, actually not n, it is something like eta, but we'll call it n. So a gradient descent, not to diverge, it should be less than 2 over lambda max. So learning rate is controlled by lambda max only, not on lambda min. But it says something like lambda min is dependent, like lambda min is, where is it? So speed is controlled by, convergence speed is controlled by lambda min. Why did it say that? Ah, but learning rate is different, convergence speed is different. So I think so. Convergence speed is something like speed depends on lambda min, which is like rate is equal to or near equal to 1 minus n times lambda min. Small lambda min, small progress. Now, real problem is go inside. You want large LR, which is, fast convergence. It needs a large lambda min. But stability forces the LR, stability forces the small LR because lambda max is large. Okay, so correct statement. We should say this, that large kappa creates a mismatch. So lambda max forces small learning rate for stability, while small lambda min makes convergence slow, causing inefficient optimization. The statement is dangerous where I said something like proportionality between LR and lambda min. It is incorrect. It should be something like lambda min, learning rate is inversely proportional to lambda max. So that would be correct. Now this is wrong because LR is not chosen based on lambda min. LR is limited by lambda max. Intuition lock-in. So think like lambda max is equals to how big steps can explode. Lambda min is all about how slow progress can be. So lambda max, how big step can explode, and lambda min is how slow progress can be. So we are defining two sort of range in between the convergence pattern. So how a big step can be taken, which can explode while converging. It might even diverge. Lambda min, well, says how much time or how much slow the progress can be. Now, quick check. I don't want to check. I just want to get on the implementation side. So if lambda max increases but lambda min stays the same, what happens? Kappa increases, obviously. Kappa decreases. No. LR can increase since it is inversely proportional. So if lambda max increases, LR should decrease. Convergence becomes faster. Well, I'll say A, something like If lambda max increases, the K increases and LR decreases. Let's give it a option also, like this is A. All right, now let's enter so that we can give it a second question's answer, which is if lambda min becomes very small, what happens? Slow convergence. Exactly. Since it's very small, gradient becomes zero. No. Li increases. No. Instability. Well, lambda max is responsible for stability or instability. So it has nothing to do with lambda min. So let's answer it as, oh, slow convergence. 3. One line explanation. So it says, explain why does scaling reduces the K? Why does scaling reduces the kappa? Shit. Where did this question come from? Like scaling, this is scaling. How does it reduce the kappa? Damn it. Why does scaling reduces kappa? Kappa is equals to lambda max upon lambda min. How does scaling affect lambda max? How does it affect lambda min? Well, I know scaling reduces kappa, but I don't know why. I think I must, increase my theoretical knowledge first. Then I don't. KNOW, not no. Good. Two are correct. One gap remains. We fix it cleanly. Then we move on. You said, I don't know. This is critical. If you don't understand this, it becomes mechanical or garbage. And it said that. Why scaling reduces kappa from first principle? Oh, not so first principle. Please, please, please. Step 1. What creates bad K? Bad kappa. Sorry, from earlier, we have Hessen's value, which is 1 over n x transpose x, and lambda I, which is variance along direction I. And now, if features are, x1 variance is 1, x2 variance is 10 to the power 6, then lambda 1 is 1, lambda 2 is this, kappa becomes 10 to the power 6 because of variance along direction I. So where is scaling? Is this scaling? So what does scaling do? I don't know. Standardization does this. X minus x mean, like this is scaling, all right. X minus mean, and then we are dividing that by rho, which is standardization. This forces the various variance of x1 and x2 to become very similar to 1, are very close to 1. Now step 3 is effect on h. Now lambda 1 is equals to 1, lambda 2 is 1. So kappa is very similar to 1. So final answer, you must be able to say that scaling reduces kappa because it equalizes the feature variance. All right. So it reduces the kappa from 10 to the power 6, which was a million, to 1 directly after, neutralizing it or scaling it, because it equalizes the feature variance, which makes the eigenvalue of h similar in magnitude. Final confirmation. Oh, don't confirm these. Oh shit. Only ask MCQs. MCQs. Why does large lambda max versus small learning rate? So let's answer them one by one. So I should say something like LR is is direct, directly, proportional, proportional to uh, lambda max, which is if L max increases, the LR should be decreased. Otherwise, big steps and explodes. So that's why it forces uh, to be small. If lambda max is increased by any chance, we should decrease the LR. Now, what does the small lambda min? Why does small lambda min the slow convergence? Lambda min is responsible for the speed of convergence. So, a small L min means a slow convergence. I think this is satisfactorily. Third, what is kappa measuring intuitively? Intuitively, kappa is a ratio, BETWEN, lambda max and L, sorry, and L min. All right. So I think since lambda max and lambda min are sort of range, so kappa is doing what? Kappa is doing what? If we say we can go from 1 to 100, and if we divide 100 by 1 and say this is a value which is 100 steps, so it is like number of range. But if we say something like we can go from 10 to 100, we are defining the range is from lambda max, let's say 10 to 100. So our step can only be 10, which doesn't make much of a sense. So k cannot be a step. K is something more profound, a ratio. But what does that represent? What does this ratio represent? So if we are going from 10 to 100 and our kappa sort of comes out to be well 10, what does that signify? It signifies something like uh, the ranges are not very far away, so they are converging properly. I think it signifies the convergence near one or greater or smaller by ratio. So it doesn't mean any step, it means how big or how small the difference between the range is. If lambda max is too great, we will see its impact on k, which will be, explode, which will sort of be great again. Like if we are going from 1 to 100, we'll see kappa become a sort of 100 times. If we see that again it is going from 10 to 100, we see kappa becomes from 100 to 10. If we do something like 90 to 100, now it becomes smaller than 1. which is, 100 divided by 90, which means 10 over 9. If we start dividing it, it will become something like 1 point. Yeah, so it is near 1, not smaller than 1, but near 1. But if we say something reciprocal, like lambda min is 100 and lambda max is, let's say, 50, then it becomes 1.2, which is 0.5. And that signifies that our speed will be, well, faster, but because of lambda, well, max, our stability might be affected. All right. So I think this is and then I'll take a water break. Good. You're now very close, but we tighten the precision. No loose language. Oh shit. Means I did something incorrect. So it says learning rate versus lambda max. Your answer LR is indirectly proportional. Big steps explodes. Well, fix wording. Well, I know we have to fix wording, but I don't want to type. I'm lazy. So correct version is like lambda max controls the maximum stable step size. So if lambda max is large, the learning rate must be small to prevent the divergence. Well, that's what I was trying to say, but it looks comical. Sure. Question 2. Lambda max and speed. So your answer is lambda min responsible for speed. Correct. Keep it. Defined version would be lambda min determines the slowest direction of progress. So small lambda min causes the slow convergence. K intuition needs sharpening. So you said ratio, which signifies convergence near 1 or greater. This is vague. We make it precise. Correct final statement will be memorize this. So kappa measures how uneven the curvature is across directions. So a large kappa means some directions are steep while others are flat because lambda max is, well, greater than lambda min by a large fraction. So yeah. So therefore, some directions are steep while others are flat if there is a large kappa, and which causes the inefficient optimization because it can take big step somewhere, a slow step somewhere. So it is like a mountain, and I've given an example of L shaped, which is like slanted L. Sometimes it takes a big large step, sometimes it doesn't. So it's very uneven. So it says log this mental model that lambda max is limits the learning rate, which is for stability. Lambda min, okay, so lambda max is responsible for stability because it limits the learning rate. Oh damn. So that was the point. All right, all right, all right. Now I get it. So lambda max is responsible for stability because it limits the learning rate. Now lambda min, well, controls the slowest progress. Okay. As for kappa, it measures the mismatch between the two by, taking the ratio and all that. Now it says you are cleared. You have now sufficient conceptual grounding. Well, I think so. Before starting out today, yeah, I think I have gained some knowledge to an extent. Now, execution list, do not skip this. So when you finish coding, you must look like this structurally. Condition number before scaling looks something like this. Condition number after scaling looks a single digit or double digit. GD unscaled, epochs is this, final loss is this. GD scaled, epochs becomes less, final loss is, well, something. Momentum. All right. Rest output should be, oh, we are also doing something in rest. So vector allocation time and slice view time and speed up. Final warning, if K doesn't drop, scaling bugs. We are actually learning today, not just code. You are learning numerical stability, optimization geometry, memory efficiency in pipelines. Now this is real ML system engineering. Next step, go implement. When done, some of the, oh, it says, well, implement by yourself. Shit. At least give me some code. No, I'm learning right now. It's not like I know everything. Well, I think I should take that in my computer, not on my browser, because that will be faster. I don't know. All right, so we are generating data set first of all. So this is now step by step. So implementation order. This is our implementation order. So this is our data.py where we are implementing, well, n equals to 10,000, and then x1 equals to numpy dot random dot ran n of n. Then we have x2, which is equals to 1,000 times the np of random dot rand randn randn. We are giving it a n, which is 10,000. Now we have a x matrix, which is equals to np dot column column stack, which is, x1 and x2, x1 and x2. Before, using np, just, import numpy at least. Import, give me some suggestions. Numpy as np. Yeah, right. Now we have to introduce noise. Noise equals to np dot random dot rand n, and we are passing n again. So these are our noise. Boom. Let's delete a space. Take another line. Now what? Now we are giving it a y. Y equals to, let's do this in a new line. Y equals to 3 times. Why are we doing this? 3 times x1 and 0.5 times x2. That's nice. Let's do it first of all. Then we'll figure out why are we doing it. Shit. Zero 0.5 x2 multiplied by x2. And then we are adding a noise to it. Right? Now we have experiments.py. So let's do that. Let's define it over here that we have experiment.py. H equals to, which is license value. We have x matrix transpose. So we have x, we have transpose of it, and we are multiplying that with our original matrix, and then we are dividing it by n, as we did, to take a mean, or what? I think mean eig, which is egg val equals to np dot lin algebra dot eig vals, and we're passing this h to this. We are creating something like, from numpy we are using linear algebra, we are creating eigen values, and we are passing edge. Well, I've never done this, so I don't know what it does. And instead of just writing k, we are writing kappa fully. We are giving it np of max. We are giving eigenvalue. We are dividing np dot minimum of eigenvalue EIG VALS. Oh, I must take some water break, please. And I'm feeling thirsty. Now we have to print before scaling and after scaling. So we have to scale it now. This is our scaling. Should we copy it, paste it, or should we just define a standardized? Should we create a scale.y or just we create scaling normally? All right, we will do it normally. So we'll say defining, std scaling standard scaling. So we define it standardize with a z, not a, not s, but z, and we pass matrix x to it. For mean, instead of making a function for blah blah blah, just returning the value of np dot mean for x with a excess of 0. We should not create another function for this stupid one-liner. Otherwise, we would have to do two-liners. Standard is equals to, we are standardizing. I don't know how it does. The NumPy implements it automatically. So we'll pass a NumPy.standard, computes the standard deviation along the specified whatever, and we'll pass the matrix x, and again x's is equals to 0. I think this specifies that this is not a scalar value. This is a vector with an array or something like that. Avoid 0. So to avoid division by 0 in standardization or scaling, we must do this, that we pass standard and we index standard is equals to 0, and we say that it should become something like 1. So we avoid it. Now we create a x scale, SCALED, and we say x is equals to x minus mean or means, it's mean for now, and we divide it by standard, and then after this we just return with a r, we return the x scale. This is it. All right, after that we should implement a gd.py as it says. Yeah, we are not defining gradient descent, we are just creating a gd.py. Just interesting things. And in real world, like if we were doing something like gd.py, we must also, sort of import these other experiment.py and data.py in our main.py. If we are doing something like this, creating 2-3 Python files. Yeah. All right. So if anyone knows how to, module it, you can go along, not go along, but just follow these steps and create gd.py or data.py and everything like that. But you must also import it like a module, and then you will be able to do this. But right now it does not. That's why we are here just in a single Jupyter file. I see some wrong indentation. Since it returns, we'll give it back the indentation. On gd.py, we implement the full batch GD. We track the loss history, gradient norms, stopping the NP linear algebra norms gradient less than 10 to the power minus 6. How do we do that? We implement full batch GD. So do we have to say define GD? Or just say GD? And what is GD? Like we know gradient descent and it is x multiplied by weight. Do we have x? Do we have 8? Ah, step 4. Momentum.py. Ah, and gd.py, we should say something like grad, not just gd. Yes, gradient, isn't it? Gradient descent. Uh, we pass the matrix x, we pass it w, and we return. Well, before that, we should define it like this, like we never wanted to, but let's do it. And we return. Eh, this return value is incorrect. So what it is suggesting is incorrect. I think so. This is what we did earlier, but where is the w right now? So that's the question. Do we have a w? We don't see any w. So let me check, isn't it? Let me check first of all. Uh, where is the collab? Collab. Where did we use Siri? Data. All right. Day 8. This is our day 8. Let's check in our day 8 how we implemented or defined GD. Mhm. See, W is there. I think in our implementation also there is W, but I don't see it right now. No, there is no W right now. No W right now. Why are we doing this? True W np.array 3 to 1.5. But over here, yeah, so W or the weight is 3 and 0.5. Oh shit. And instead of doing it like this, we should have done something like x, matrix multiplied by true W, which is also sort of a matrix or array. And then where is our descent or gradient? Grad. So this is our gradient descent. 2 over n n samples, which is our n, our n is this much. So we just say that. Let's do this. As for W, we don't have a W. Let's define the W as 3 and 0.5. Or let's not do that for now. Let's not do that for now. Uh, all right. And this was wrong because this was not a definition of gradient descent. This was for prediction. I remembered this now. Yeah, it was for prediction. We predicted x at the rate w, and then we minus with the actual y, which was, yeah, crazy, crazy, crazy. So let's keep that in mind and then follow along. We should multiply it with x transpose, and we had 2 over n, which is what? Well, which is the samples. Value is 10,000 for now. And there's some problem. It says, oh, multiply. So we have to say, well, multiply. I don't see much of problem now. xt at the rate. Yeah, again, multiply, but I made a num by 1. Yeah. I think this is all right, like workable. with. This can work. So this is a gd.py, but it also says something like track loss history, created norm or normalization. I don't know. Then it says stopping at np.linear algebra norms create, uh, which is what linear algebra is used here, but never as a normalization. So a momentum.py. Let's do that. Shall we? momentum.py. So we first of all say momentum is 0, and then for e for we say gradient is equals to gradient descent for x and w. We are not passing what the w is right now because we don't know what the w is. And then we have a v, which is beta multiplied by the same formula. And it seems there are few problems. First of all, w is not there. Second of all, no lr is defined. Third of all, no beta. So yeah, few problems. Now experiment.py, run 3 experiments, gd scaled, unscaled, and all these things. Now I've tried implementing on my own. I'll say give me step by step, give me step by step instructions. Like here is my progress in the pie. Oh, and then I'll paste my pie code. But before that, let's see what it said earlier. So condition numbers before scaling is something like this. Oh, so we have to do what the experiment.py said. So we'll create experiment.py, experiment.py, and we'll experiment with all of these. But first of all, copy it. Let's paste it over here, and I'll take a break. But my computer just hanged right now, so I can't. It says no partial work, but well, we never defined what the work should be. I'm not that great all of a sudden in just day 9. Good. You have started, but this code will not produce valid results yet. I know because a few missing parameters. Do not jump ahead. We will fix it step by step. Do not jump ahead. So first of all, noise and all these. But before that, let's take a break. All right, shall we? So I think over here, mute it. So we are back. I hope it's recording perfectly. Sometimes it doesn't. All right. So we were at fixing our code. So well, it says our code has multiple errors. Actually, we knew because it indicates we have errors. We don't have a W. We don't have epoch. So yeah, think about that. We don't even have epoch. So yeah. So first error we see is np.random and rand_n. Fix is, well, oh, spelling of random is incorrect. All right, let's do that. random, random. Where is this noise? random, random. All right, this is correct now. Error 2, k computation. So you wrote kappa is np.max and then eigenvalue divided by minimum eigenvalue. Okay, So that must have happened due to some error, but this is kappa, absolutely, isn't it? And now what's next? Fixed data or pi structure. So right now the variable are global but design. Yeah. So instead, we should pack this in, well, a generate dot py. Sorry, not generate dot py, but define something like g and generate generate data, and then pass the n uh, and the default value if n is not declared, but it is, so no effect whatsoever. This is our default value for n. And then we say it like this. And second thing, move this before, like this. N is equals to 1000, and we'll pass that in. Do we need it? Actually, we don't. Let's keep it capital N because it's a constant. So now generate data is done. We should return x and y. So yeah, return first of all x and y, and then it suggests x comma y generate data of n. All right. Now step 2, moving to scaling.py. Where is our scaling.py? Scaling.py. Where is it? Standard scaling. Yeah, over here. Create scaling.py. We shall do that. So instead of doing all this right here, well, scaling.py is like exactly this. So we don't actually need to create scaling.py, but let's change the comment. Instead of just defining, we'll say we are creating scaling.py, scaling.py. Rest the code is same. Import numpy, define standardize, and then x, then mean is there, a standard is there, standard then index. If the standard is 0, then we are making it 1 is there. Then we are returning the x scaled, exactly the same. Step 3, it says fix the gradient function critical. So this is our gradient function. What is wrong with this? I don't think much of anything is wrong with this. We are passing x and w, and I don't see any problem. So it says y not passed. All right, so y is not passed. So this is our first mistake. So let's pass y also like this. And n is not defined. Exactly. So how do we define it? We say n is whatever the shape of x matrix is. N is x matrix dot shape, and 0, why 0? Because the 0th index is 10,000, isn't it? And the 1th index will be the features. That will be, let's say, 2 or 3, whatever. Now it says, well, step 4, implement the full GD loop. So this was our gradient descent. No, this was our compute gradient, isn't it? So we'll say this is a compute gradient, and it should be compute, compute gradient, compute gradient, and then this is 1 over n, and still no squared. So I don't know what happens. We have a gradient descent which takes the x, y, lr, and max epochs. Compute gradient, and this is a gradient descent. So let's write it now. Let's define the gradient descent, gradient descent, which will take first of all X matrix, then the Y, and then LR, and we'll say the LR is default value of LR is 10 to the power minus 6. That's what E means, isn't it? It's base 10, so 10 to the power minus 6. And then we'll pass the max epochs, or just epochs, but let's say max epochs. How about just say epochs, isn't it? Or are we going to do something like, no, so we are not doing anything for epoch. So we'll say epochs for now. EPOCHS, because that matches our previous codes where we just defined epochs instead of max epochs. And now we say, we take N and D, which was present in X dot shape. So what happens is X0, so which is 10,000, will come in N, and D, which is how many number of features, let's say 2 or 3. I don't think I've defined it yet. Will come in D, all right, or F. But since here we are saying D, let's keep it D. W is now weight, is now NP initialized with zeros. So zeros and with the size of D, all right, which means 3 or 2, like whatever the features are. That should be the size of our weight. Now loss history, we are creating an empty array, or sort of creating an array and initializing it as empty. We can say save anyways. And now we are creating a loop where we'll do the epoch like this instead of writing it like this. We are doing it perfectly. Are we implementing the momentum here only? We are not. I don't see any implementation of momentum. All right, so I think we'll do that in next fix. But before that, let's make this properly. So for epoch in range of epochs, EPOCHS. If I do +1, well, if we are doing 1,000 epochs, we'll see the 1,000 actually, and we might see the errors. We know why we do epochs +1, but if I do that, GPT will say it's wrong and all that. I don't want it to say wrong, but it's not wrong. It's just GPT doesn't know something that we know. Yeah, it'll run for like 1,001 epochs, but does it matter? Not much. Just one step more. X transpose. Why are we saying something like gradient is equals to gradient? Why can't we just pass the whole gradient to compute gradient? It'll do the same. Let's do that. Otherwise, why did we even create the compute gradient? Isn't it? So let's do that instead of writing down the formula. We'll say compute gradient, and we'll pass X. Oh, let's not to move ahead of ourselves. Now X is there. We have X, we have Y, and we have W. Yeah, exactly. So we can do this. It's all right. Then it says after gradient, we have to compute our loss. So we'll create, oh, where will we create? Here we'll create, first of all, compute our loss, and then we'll say loss. Wait a second. I don't want to see this. Now we'll say loss equals to what? This is our new formula that we saw. There was, instead of just 1 over n, we saw 1 over 2n. Why? Well, because of linear algebra normalization. I don't know why, but it was there. So we are going to just do it. Just do it. We'll understand the reasoning behind, like after few days, or likely tomorrow, or today only. We don't know yet, but that happens sometimes. Np dot linear algebra dot normalization, so norm, and we are passing x matrix multiplied by w, and then we are minusing y, and then power 2, so power of 2. This is our loss. We are penalizing our loss by, well, power of 2, but I don't know why what we'll get with this linear algebra normalization. I don't know that. And second thing, why are we dividing 1 by 2 also? Like 1 by n is known, but why 1 by 2? Like, I don't know. Then we have loss history, and we are, on this array, we are appending the loss that we are calculating over here. So we write it down. Loss history dot append, and we are appending the loss. All right. Then what? Then I see that we have a stopping condition. It suggested we should have a stopping condition. STOPING, stopping, well, condition. So CONTILON condition. And we say in a if statement that if linear algebra dot normalization of grad or gradient goes something beyond uh, 10 to the power minus 6, we should stop. So we break. Exactly. Otherwise, we'll go normally and we'll update the weight. We can write it like this as it suggested, or we can just directly say minus equals to as a shorthand. Ella, we also did this everywhere, so it's not different for us. We know why we did this. And finally, we return the W, loss history, and epochs. Why epochs? Why are we returning epochs? I think this implementation requires you to return epochs because we're going to, I don't know, we'll print it or what. So we'll just, return what it says we must return. W and loss history and epochs. This is something that we never did. Now we are returning epochs. We'll just use that to, print it. Now fix the momentum, which is, this one, momentum.py. So your version is incomplete where v is 0. We are initializing it with 0, but for epoch we can run this. So missing is the initialization of weight, which is np.zeros that we did in epochs, and loop definition, stopping condition, shape of v, which we did over here. So I think instead of directly passing everything, we'll just add this line, which is v is beta multiplied with everything. But what is beta? So yeah, and we must also pass beta inside this gradient descent, or else we must just calculate what the beta is. So let's see what the acha. So we are creating a normal gradient descent, and then we are creating a momentum gradient descent. So we have two types of gradient descent. So let's do it normally. What normally? But like, let's create it again. We'll create or define momentum GD, which is gradient descent, and then we'll pass x, we'll pass y to it, we'll pass LR, and by default it will be 1e minus 6, which means 10 to the power minus 6. Then we'll have beta. Oh, so we have to pass beta, isn't it? So beta is 0.9, and then max epochs is like max, and then epochs epochs is equals to 10,000. Exactly. Then we say that n comma d, we are getting that from x dot shape. So x dot shape 0 will index back to n, and 1 will index back to d, which is, number, which is 10,000. D is features, which might be 3, 4, whatever. We have not yet defined the features. We have still not defined features for now. Nothing wrong with this, but still. So while calling it, we must have to, well, define it. So we are initializing w or weight as a numpy dot zeros with a size of d, which is 2, 3, whatever, how many features are there. And then v, which is momentum, is again same as, weights shape, which is np dot 0 d, same shape. Loss history is again same, not loss, but loss history. Loss history is same. And then we run our loop for epoch. Oh, so we defined max epoch over here. We shouldn't. We should just say epochs, isn't it? Wait a second, wait a second. So we are returning the epoch. Why are we returning the epoch? Oh, so we are actually returning this one epoch. I don't understand this yet. We must see the implementation first, and then we can start guessing around, like what is happening. Array and GE, but epoch and epochs should not, combine together or get mismatched in this confusing world of a code. Yeah, there is S to it, and we are not returning epochs. We are returning epoch. So we are passing epochs, but we are returning epoch, which is this. And I don't know why we are doing that, but let's do that. Then we have gradient is equals to, again, the same formula, but we'll just use the grad descent, no, compute grad, no, compute gradient, x or w and y. We have x, which is passed through momentum, gd. We have y, which is passed again. We have w, we have declared it over here, so it works. So we have gradient. Then we have v equals to, the momentum equals to beta multiplied with b, multiplied with v, and then we are adding the grad, not just lr into grad. So this is wrong, but why is it doing this? I don't know. This was wrong. Sometimes the suggestions can be funny because one stops us from doing that, and another, well, suggests it to us. All right, so this is our calculation now, p and w. Now what? Now we'll calculate the loss, which is equals to, well, again, the same for 1 over 2n. So we'll say 1 over 2 and multiply, which is asterisk n. And then we have asterisk of np dot linear algebra dot what? Normalization. And we are passing x matrix. We are multiplying that with w, which is weight. We are subtracting y from it, and we are squaring it. So to the power of 2. Then we store that in lost history dot append, and we are appending the loss. Loss history. Oh, so that's why we are getting this yellow line. It's not lost history, it's loss history. All right. And then we again do the same thing, same condition where it breaks for linear algebra normalization of grad. If it is, well, if it is less than 10 to the power minus 6, it's great. No, if it's less than 10 to the power minus 6, it should break. Now we are returning again. We are returning after this for loop. We are saying return W. Oh, return W loss history and epoch. Not epochs, but epoch. Now we have to implement our experiment.py. So this is our proper experiment.py. So in this, we are importing all of these files that we might have created, momentum.py and all those. So we are how are we importing this? So in momentum.py, we are declaring it by like saying from momentum, not .py, but just momentum. We are importing the function momentum GD. That's how we do it. That's how we do it. But since it's just, a single Jupyter file, we'll just say something like, yeah, generate data, and we'll implement everything. GENERATE data, generate data. We'll say x comma y is equals to GE, NERATE, generate data. And this is a function, so we'll call it like this. What generate data does, well, it takes nothing except for n, so we have to pass the n. Otherwise, if we don't, it automatically takes the default value. But since we have the n, we can take this, cut it from here, we can define it over here, just above generate data. We'll say this is our n, so that we can even increase it to a million, let's say, isn't it? So we'll say this is our n, we'll pass that n. So this is our x and y. Then our n, is x dot shape, or we can just say n is equals to n, but x dot shape 0. We can just use capital N, but it would be better to just use n from, whatever the sort of metrics we are getting based on that. Now condition number before and scale, then condition number after, and then GD, then momentum, then we are printing everything. Damn. Let's do that. So this is condition number and before. What happened? Oh, control. So I pressed control. So that's what happened. Where were we? What happened? Oh, date. We also changed something. So condition number before, 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 and we must say that Heisen's equation is this, which is x transpose multiplied with the matrix of x, and then we are taking the mean, so we are dividing by n. This is a n. Oh, don't disturb me. EIG vals. Eigenvalues is np dot linear algebra dot EIG vals, eigenvals, and then we are passing h to it. Don't disturb me. eigenval linear algebra eigen. Exactly. This is the same. A kappa, kappa before is something like np dot maximum eigenvalue or EIGVALS, and we divide that with the minimum, that is np dot minimum EIGVALS. So minimum eigenvalues. Don't disturb me. Well, I hate this auto suggestions when we don't need it. When we need it, we should have some keywords so that we can call some auto suggestions. But when we don't, well, I really mean we don't need auto suggestions and these talks. Now scale. All right. So x and scaled is equals to, now we run standardize x matrix and place that in x scaled, because that's what we get returned from this standardized function that we defined. Where is this? Yeah. So we return what? We return x scaled, isn't it? So we are storing that in x scaled variable. X scaled is equals to standardize with a z, standardize what? The matrix x and get the x scale. So we have scale. Now we should have another condition number after. So condition number, and let's say after. Now we should calculate again, which is h scaled. Now h scaled, h scaled. Now this should be, what was h? H was Hessen's value, where we take x matrix and multiply it with, transpose of it. But what we are doing right now is taking the, instead of taking x, normal x, we are taking the scaled x, which, is standardized. So let's pass that as an x scaled. We transpose this first, then we multiply it with the matrix x scaled, SCALED. This is what we do. And we divide this with n. Exactly. Now don't disturb me again. Eigenvalue EIGVALS scaled, because we are doing everything scaled now. Eigenvalue SCALED. Exactly. Eigenvalue scaled will become something like np dot linear algebra dot normalize what? The h scaled, not just h, but the, don't disturb me, scaled version of h scaled. All right. And then we say kappa after, kappa after, not before, but after, or scaled. What do we say? Kappa after, not scaled. AFTER. And we define it with np dot max, don't disturb me. And now we, instead of taking eigenvalues, we are taking the eigenvalue scaled. So yeah, we are taking this and we divide this with minimum. So minimum of EIG val and scale. Exactly. Now condition number after is complete. Now we do the GD. So let's do the GD, which is gradient descent. So our W1 and loss 1 and E1, which is epoch 1. I don't know why we are returning this. Let's do that. Epoch 1 is gradient descent, and we are passing the x, normal x, we are passing the normal y, we are passing the LR as 10 to the power minus 9, 10 to the power minus 9. All right. So this is our first statement, second one W2 and loss 2, and then similarly E2, just epoch 2 is equals to gradient descent, where we are passing scaled version of it. So gradient descent, I'm passing just the scale version, and then we'll use the momentum or momentum descent, isn't it? Yeah, momentum GD, momentum gradient descent. X SCALED, we're passing the normal Y, then we are passing the LR rate, which is 10 to the power 10 to the power minus 2. Okay. Now GD is done, so we'll create a momentum. OMENTUM, momentum is W3, loss 3, and E3 is equals to momentum GD. We are passing X scaled, and we'll pass Y, and we'll pass LR, which is equals to 10 to the power minus 2. Okay. Now just printing all these stuffs. So print. Now I don't think I should just, write all these printing statements because it doesn't make much of sense. These are not logic. Oh shit, I pressed elements. So for printing statements, let's just copy it and print it. What's important is, first of all, we are printing the kappa before, which is, normal kappa before any condition number, like normal kappa before from condition number normal one, not scaled one. Then we are printing kappa after, which is condition number, which is after scaling. Then we are printing the GD unscaled. So first of all, epochs is like E1, and the final loss will be loss 1. And what we are doing is, since loss 1 is an array, to take the mean of it, we just do, instead of taking it index by index and creating a mean, we have a functionality that we can just directly write -1. We'll get a mean of it. That's what we are doing in NumPy. Same over here with E2, same with E3. All right. So we are seeing the epochs, or number of epochs, and that's it. So let's run it and see what do we get. So condition number before scaling was, well, this much. After scaling, it, well, not nearly became 1, but became 1 in itself, which is truly mind-boggling. So a normal GD, see the loss, which is quite a lot. With the epoch of, well, how did it got so much of epochs? Like, what was the normal epoch that we should have gotten? Where is it? Well, it's not here, but here somewhere. What's the number of epochs? Uh, uh-huh, uh-huh. Epoch is 10,000, isn't it? 10,000 by default. And we are calling, when we are calling them, we are calling them where? We are calling them over here somewhere. Yeah. Then we are also passing, oh, we are not passing any sort of epoch. So it's taking that by default number, which is, 10,000. But then why do we get this? It's so confusing right now. Oh, no, no, it's not confusing at all. Why? Because we are actually breaking the loop. We are not running for the whole loop. We are actually breaking it when this gradient of this satisfied this condition, we are actually breaking this loop. So a normal GD, well, had a lots of epochs, nearly 10,000, but this GD, well, it had less than this epoch. So in less epochs, we get loss, which was significantly lower than 5, just 0.5. Whereas the similar loss over here, similar or same? No, similar. It is different, but it is very similar, like very close. Till 2.9, it is very close. Then 2.5, it becomes 2.6 over here, right? So from here, it was very close, but this is a lot less loss. So compared to this, in some degree, this is less loss. This is greater loss than this. So GD scaled, well, in 1094, 1994 returns, 1994 return epochs, it sort of had a final loss, which exceeded by some values when we had a momentum scale which had a lot less, like lot less, 3 to 4 times less epochs, whereas the final loss is also a less uh, by I don't know how much of a tenth this value is. But yeah, it is less than this in just 344 epochs. Epochs is like, think of it as round. So let's say you have to make 6 apps, 6 packs apps. All right. Somebody will say, well, run 10,000 miles. Let's say 10,000 epochs, 10,000 rounds, and you will get a 6 pack apps. Uh, well, if you're efficient enough, your metabolism is strong, you'll say, well, just 900 laps is enough. Somebody might say, well, only 300 laps is needed. So who is more efficient in terms of, well, getting the result, which is creating 6 pack apps, not just whatever the side effect might be? Well, it is lesser number of rounds, or the person who is getting well jacked early. So yeah. So compared to that, well, someone in less epoch with a less well final loss is considered great. So momentum scale is good. So let's give it our code, which is this. Let's send it. Before that, let's read this. So it says critical hyperparameter note. So it says you must adjust the LR. Case unscaled, LR is very small, which is 10 to the power minus 9 or smaller. Scale LR is 10 to the power minus 2 or minus 3. So we have to do two sort of cases. Unscaled LR is, well, very small, and in scale it is larger. That's why we get in GD also, like gradient descent, normal gradient descent also, because of LR was great, we actually get this. Final check before you run. Why does, well, I already ran. So why does unscaled GD need a tiny learning rate? Unscaled GD needs a tiny learning rate. Why? Because of its range, like minimum and maximum lambdas. Shall I answer them or just paste my code? Unscaled GD needs tiny learning rate. Why? It needs tiny GINY LR because of the large uh, lambda LAMBDA max, which is not normalized yet. That's why. So two, why the scale GD uses a larger learning rate. Two, that is since the lambda max has been PROPERLY standardized or scale, we can increase. I don't know my wordings, but in my mind, I know the reason. So increase the what? Increase the learning rate. So it's like learning rate is you know inversely proportional to lambda max. So if lambda max is very large, you cannot make the learning rate also large because then it will explode. So if lambda max is very large, you should make the LR small. And if it's standardized, which means lambda max has been reduced, then we can increase the LR, INCR, EASE. So that's the concept. I think it's in my mind, but as for wordings, but it can be shallow. Yes, I just want this to be over with. Why do we use y after scaling x? Why do we use the same y after scaling x? Well, because what is y, first of all? Y is not a data set, it is our benchmark. Like we are comparing against y, isn't that? No, no. Y. Why is the y same? Why is the y same? Is there any history for that? Why is the y same? So this is our y, which is, we're taking the x1, x2, uh, multiplying with 3, 0.5. Y is our y same. After scaling x. Well, what I think can be the reason is scaling x. We are doing that so that we can reduce our, well, you know, the lambda max, and y does not do that. So I don't think y is required. Oh, this experiment.py is getting few errors, but I didn't got them. And now it is also hanging here. So let's run it. We got, well, our response, no errors at all. But there were some yellow lines, like right over here. X is not defined. Well, it is. Not here, but yeah. Why are we even doing this? Because we do this somewhere else, like down there. So let's first of all remove these three lines, right? Let's remove these three lines like this. We have scaling.py, gd.py. Over after this, we have experiment.py. So yeah. It runs properly, no errors. Let's copy our code. Since y doesn't affect our LR and L max that much, so use the same. plus its small size. SIZA. Now let's paste our program and then the output. Yeah. If I'm not wrong, my OBS is using most of the CPU, which is well 40%. Not bad. The rest of them ML is getting utilized by browsers. So this is strong work. You achieved the intended numerical behavior, and now we refine the correctness and eliminate the hidden bugs. Result analysis is important. So before number, like before is 1 10 to the power minus 6. Oh, it's wrong. Like, is it? And then after is 1. Is it talking about this one? 1, 2, 3. Yeah, it is nearly about 10 to the power 6, not minus 6. Perfect. Scaling worked exactly as expected. So it says convergence, which was, methods like which converged fast. So, well, the GD unscaled for nearly 10,000 epochs. Its losses were 4.95, which is significant. For GD scaled, where we sort of standardized it for 2,000 epochs or like 1994, 2,000 epochs, we had a loss of about 1.098, which is again significant, but not that much. Like, how did it increase suddenly? Let's run it again. Will we see a different? Yeah, so it changes time and again for each epochs. And the momentum, well, for 344, nearly 1098. All right. The loss sometimes reduces, sometimes doesn't. But for this one, well, it reduces always. See, this fluctuates damn too much. Like, why? Why? See, this is now, well, greater. Like the loss is now greater than the normal unscaled one. This is bad. It keeps on increasing. Why the hell it keeps on increasing? Ah, now this seems something that we wanted. So it says unscaled is slow, scaled is faster, momentum much faster. This validates your understanding, but critical bugs. So you gotta correct results despite wrong code. So there is something wrong. Fix them now. Kappa after scaling, serious. You wrote something like, yeah, completely wrong. You are computing the matrix norm, not eigenvalues. Okay. It says fix this by doing nothing. Like what changed between these two? Well, can someone tell me what exactly changed between these two? Everything looks the same. Oh, normalize and eigen. Oh shit. That's why it was fluctuating. Shit. Eigenvalue scaled over here. Instead of saying, oh shit, yeah, don't suggest me I hate it. Instead of normalizing it, well, we should have said something like eigenvalue. So we'll say EIGVALS. So eigenvalues, and then we are passing h scaled. Perfectly normal. Eigenvalues is, well, correct. I think there is rest, there is no problem. So this is fixed. Why your results still look correct? Because for near, you know, identity matrix, which is normalization to 1, so I got lucky. Well, another time I didn't. Shit. Well, this breaks. So yeah, there is something like overwriting GD results. So you wrote something like you overwrote the W1. Fixes, do this. Well, I don't see. Oh shit. W1 and W1. Same. Yeah. Such carelessness is not acceptable. I think. Oh, there are more bugs to come. So bug 3 is like momentum.py. Where is momentum? This is momentum, but momentum.py, where is this? Yeah, over here. It says grad compute gradient descent. Yeah, exactly. Not imported. Well, don't need to, because yeah, the concept answers subtle but important. You said why doesn't affect LR and lambda max much, not precise. Correct reasoning is why does not affect the Hazen's. Oh, yeah, not same, but still very close. So not affect the Hazen's value, which is x transpose of x, because we are doing everything with x. We don't even include a y. So it does not include sort of affect the eigenvalues or conditioning or condition numbers. System level insight, which is very important. You just demonstrated before scaling, which is, so no sort of error was there in momentum.py, because we are not creating a different momentum.py. But if we did, we should, import a compute gradient from the gd.py, isn't it? All right. Our system level insight, very important. So you just demonstrated like before scaling, which is k nearly equal to 10 to the power 6. LR must be tiny, which is slow. After scaling, which is 1, LR can be large, fast. So this is not just ML, this is numerical preconditioning. Scaling is equals to primitive form of preconditioning. Final test, you must pass. Deep check. Why does moment? After that, what happens? After these, me move to Rust. Zero copy public. Oh, whoa. So do we have to? Oh, shit. So I think I'll have to copy and paste this as a, Python in, well, my Day9. And, well, I think I'll need to rethink how I do stuff in my project learn. Like project learn, then there is Python and Rust. I separated it. I shouldn't have. Why? Because now I have to now integrate. So I have to make directory over here called Day9. Inside that we will have Rust and Py. So inside that we will have make directory Python and Rust. So that, yeah, because initially, like, our final result was something where we can integrate Python and Rust together and use the Rust level, low level computing, and Python's high level just management and user interface sort of. So now I think I'll have to create all these experiments.py. So let's do that. Let's do that. And finally, we'll run it. Python only. So let's cd into Python before answering them. Let's vim what? Vim data.py. Data. Oh shit. Before that, let's do one more thing. Python dash m. Let's create a virtual environment over here. Or shall we do it before this? At the starting, like over here. Let's create it over here. Python dash m venv. Let's call it venv. Now source are sort of activated. It takes time. Source the venv bin activate. Exactly. Now we'll create, first of all, inside Python, we'll create what? Data.py. So we'll do data.py. Now instead of writing it, well, I don't want to write. So I'll just copy and paste it. We do this, we close it. It's done. Now scaling.py. We have to create another thing called scaling.py. As for all these imports and all those things, well, we'll do that separately. Like, let's just first copy the codes and create the modules. This is our standardized scaling.py. Now we have gd.py. So let's do that. This is a gd.py. gd.py. Let's paste it. Now momentum.py. momentum.py. Oh, momentum.py. Exactly. Now there's only experiment.py left. So from gd import import, import what? Compute descent, isn't it? Compute gradient. compute gradient. Exactly. Then what? We have experiment.py. Let's first of all close it, isn't it? Let's close it for now. We'll do that later on. Now this is our experiment.py. If this experiment.py runs, then I think we have done everything correctly. So vim experiment.py. Yeah, we'll save it. But for experiment.py, we have to do multiple things like import all these libraries. So let's say from gd, we have gd, isn't it? From we have data. From we have what? I need help. No need to. Just see all these. We have gd, momentum, scaling. All right. We have data, gd. Let's go for momentum. 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 We have scaling, scaling. And let's import everything. So import everything, shall we? Yeah, import everything, import everything, and import everything. Uh, Now at the top, let's import something precious. Oh shit. Precious import numpy as np. Is this good? Good work. Let's try running Python and experiments.py. First of all, no module called numpy. And second of all, well, I did not import numpy in other required files. So let's first of all check all of them. So starting from data.py. Does it require anything? No, numpy is there, so satisfied. Good. Now, vim scaling.py, does it require anything? Yeah, it does require numpy. So we'll say import import and numpy as np. I think it's correct. So we'll just move on. We'll see scaling after scaling. We have gd. So gd.py, does it have numpy? No. It requires one? Yes. So we'll create import numpy as np. All right, we have gd. Let's see another thing. After gd, we have momentum. Yeah, we need numpy, so we'll say import numpy as np. No problem. As for this one, x numpy.np gd. Now I think everything is done. Just pip install numpy. That's it. Pip install numpy. Oh, numpy. So this is the first time where we are well creating a Python file in our directly environment. So it just installed it. Pip install upgrade pip. Now if we see pip list, let's see both of them. Pip, which is 26, which is the new version, and numpy, which is 2.4.3. All right, now let's clear it all. Let's try running our Python experiment.py. No problem. Oh shit. Oh damn. Spelling mistake. So let's say experiment.py, isn't it? And this is correct, but in momentum.py, instead of from, I said form. So let's see w from. Oh, it's correct. Let's try running it again. Oh, yeah, run it again. So we got our results. We got our good results. Now I think we can move on to answering the questions it asked me, and then we'll move on to Rust pipeline where we'll use this whatever we created. So yeah. So first question is deep check. Let's close this, shall we? Or shall we not? Well, we'll close this day 8 instead. And we'll use vertical tabs because we like vertical tabs. And thing to note over here is it is not using MCQ to ask questions. MCQ, MCQ, EMCQ. Recheck. Why does momentum converge faster after scaling, not before? Momentum converge faster after scaling because after SCALIMG, the lambda max is less, so a higher learning rate. Therefore, it's faster, isn't it? Oh shit, it's hanged. Still, it's hanging. I don't want it to hang. Code reasoning. If you accidentally standardize incorrectly, like and P standardized X, well, it doesn't look very incorrect to me, but it is. Why? Standardize. So for standardization, we actually used our own formula of X minus mean and then divided by STD. So can we do this instead? What happens to A? What happens to kappa? Uh, I've never done this NumPy standardization, so I don't know. I don't know what this NP implementation of well standardization does to X, or is is it any different from our our own STANDI standardize function? What happens to kappa? I assume kappa becomes 1. 3. System thinking. Which is more important? Better optimizer, which is momentum, or better conditioning, which is scaling? Well, I think both. I think both. So that after scaling, we can use large LRs and momentum in, well, it does what? It increases the LR too. So win-win for us. I don't see any downsides. So yeah, I'll answer it like this only. That it is win-win for us. As for if there is any downside of using both, I don't know yet. Because I've been introduced to it like right now. And let's check another thing. Like we have our own functionality of pdump. So does it work? Or can it copy all the Python files with their names? So let's create another. Well, free. Let's dump it. It does not well copies the file content. Why it doesn't? So let's save it and close it. All right, we have a tree. What shall we do? We shall see if there is another version of pdump for tree. Pdump here. And instead of vim, we use cat and we see tree. Is it related to our code? Well, no, but it's important for me. Yeah, this pdump is similarly trash. So what can we do instead? Can we use mdump? But that is for well, that is for our Trump. That is for MD files, so I don't think it will be able to use it. And if I try pasting it, oh, what did we get? Quit, quit, quit. Cancel, cancel. Let's paste it. Paste. So yeah, it gives us a tree and doesn't copy any file contents. So trash. We don't have any sort of dump left. Do we? F dump. I guess we have F dump. Let's see. F dump. Any dump. Any dump. I think it's not here. So clear it. Let's clear it. Instead, let's use our, well, let's use our dump from anywhere else, which is, well, in my dot files. Yeah, dot files. In scripts, we have, yeah, we have pdump. So let's try this pdump. Is it different or is it the same? Trash. I hope it's different. Paste. It's not. It's trash. Control D. Control D. It's trash. It's trash. It's trash. How about instead of pdump, we can't use mdump, so we have another dump which is fdump. Let's try using that. Cat tree. Is this workable? This is working. But I can't even. Control D. Let's open the tree like this. But I don't think it has even copied anything. Full copy to the clipboard. But it didn't. So shame on you. Well, now I have to look at these script files. They're bash scripts, so nobody mostly likes them, but it is likable sometimes. Yeah, see, this double copy is doing what? Let's not get into this first of all. So we've answered it, and it says incorrect, incomplete, and slightly misleading. All right. So you've got the direction, but there are still some conceptual inaccuracies. So we tighten them now, and this is the difference between it works and I understand why it works. So question one, momentum after scaling. So you answer after scaling, lambda max is less, and the higher LR, the faster. Incomplete and slightly misleading. Correct. Well, the correct explanation would be that momentum helps when gradients are consistent across steps. In ill-conditioned problem where the gradient oscillates due to large lambda max, so momentum cancels itself. After scaling, the gradients align better, so momentum accumulates and accelerate convergence. Again. Momentum helps the gradient. Momentum helps when gradients are consistent across steps. So in ill-conditioned problem gradient, in ill-conditioned problems, gradient oscillates due to large lambda max. So the momentum cancels itself. After scaling, the gradients align better. So momentum accumulates and accelerates convergence. So key insight is before scaling, gradient direction was like oscillating forward, backward, forward, backward, forward, backward, oscillating. Momentum cancels inactive, so it becomes ineffective. After scaling, the directions of gradient, well, it aligns. So momentum accumulates faster. Oh, so that what happens. So before scaling, gradient direction is like spread out everywhere, forward, backward, side, left, everywhere, which is oscillating. But after scaling, we align it, and after that, momentum accumulates faster. Question 2 is incorrect standardization. You said, I assume K becomes 1. This is wrong. What this code does, well, I didn't know what this code does, but let's see. This computes one scalar for entire matrix, not per feature. So effect, you divide, so only one scalar. So what that one scalar can be, when you want to standardize, we want it to be 1, a near 1. So if it does compute for one scalar for the entire matrix, I am not wrong if I say it's 1. Uh, well, for per feature, it differs. Effect is that you divide both features by the same number. So x1 remains unchanged scale. It was 1. X2 still huge relative to x1. The result is that variance of x1 is now lesser, like far lesser than variance of x2. So eigenvalue still far apart. K remains large. So this happens when we do this, that the variance is still the same because x1 is unchanged, whereas x2 is still huge relative to x1. So yeah, nothing changed. Eigenvalue is still far apart and k remains large. Correct answer would be k remains large because feature-wise variance imbalance is not corrected. Well, we'll need time to digest this first of all because there's a lot. Now question 3, optimizer versus conditioning. You said both momentum increases the LR. Both momentum increases the LR. Incorrect. Momentum does not increase the LR. Well, yeah, it does not. It just works when everything is scaled properly. So correct answer would be conditioning is more fundamental. Without good conditioning, even advanced optimizer struggles. So optimizer like momentum improves convergence only after problem is well conditioned. Priority hierarchy is something like conditioning, scaling, foundationals. If it asks me again this question, because I'm again going to answer it wrong, so I'll just say give me MCQs instead, because there are far less chances of giving an incorrect answer at MCQs rather than just wording it out by yourself. So priority hierarchy is conditioning, which is scaling, is foundational, optimizer momentum, enhancement. Log this in. Concept is scaling, a role is fixes geometry. Momentum exploits good geometry. Bad geometry breaks everything. You passed Python section and you understand conditioning, eigenvalue, GD dynamics, momentum behavior. This is not beginner level anymore. Next, Rust, zero copy pipeline. Concept 2, we switch domains. Before coding, answer this. If you create a new vector for every batch, what happens to CPU usage, memory bandwidth, and cache efficiency? For every batch, new vector. Like for every batch means for 1,000 epochs, we need 1,000 batches. So mm, memory bandwidth, CPU is like affected the least. Uh, let's go first of all, 1, and we are answering 1. So A, aha, it's hanged. Shall I take a break? Nah. A, CPU is for calculation, so remain mains the same probably. B, what happens to memory? MEM. Now because of vector is generated every batch, we have many vectors in memory, which is what? Which becomes the bottleneck and takes much more space because of pointers of vector. As for cache efficiency, I think vectors are stored contiguously in Rust. So let's say CHACHE. I think even the vectors are stored contiguously. Vector R नहीं vector store, vector stores element, vector stores element stores el contiguously. So CACHEEFFECIENT. There are many spelling mistakes. I admit that. I can't change it because it's hanging down too much. So if I waste that much time, it is time wasted. Now, why is the reference of F64, which is again a pointer of a floating number of 64 bits or bits, the slice faster than a vector of F64 batching? Why is that the reference of F64 slice faster than a vector of F64 batching? So it says we have an array reference of F64. F64, it is array REFF of type F64. It slices faster than vector because the way it is defined. Like what way is it defined that it is, slicing faster than vector of 64? Arrays are easier to index and therefore easier to slice. As for vectors, I don't know. Like I've never sliced a vector, so I actually don't know. Don't know. Sorry. Now question 3, and it asks us that what does a lifetime guarantees in this one. So it says that this, it says that this structure data set will have a lifetime of dash a. It can not be exceed it in GENERIC and OTATION because of these. What are these? These brackets. Any else? Anything else? No. Shall I take a break? I think I should. Let's first of all, see these answers and then I'll take a break. Right. You're thinking in the right direction, but your answers are partially incorrect and lack system level precision. Well, it does. Fix that now. So, vector per batch impacts your answer need correction. So, CPU, you said same, wrong. CPU usage increases significantly because of allocation. Oh, shit. Allocation plus copying happening every batch or happens every batch. Now each batch allocates memory with vector with capacity, whatever the capacity, then data copy or copy data, mem cpy, then deallocate later. Now this is extra work, not just computation. Yeah, it is. So memory, you said many vectors, bottleneck, correct direction, but refines. Frequent allocation causes the memory fragmentation and pressure on allocators, increasing the latency. Also, the temporary buffers, which is churn, allocator overhead, non-trivia caches that you said vector is contiguous. So fine. Well, it is also wrong. This misses the real issue, that the copying data into new vectors destroys the cache locality because data is repeatedly moved instead of reused in place. Oh, for every batch, exactly. So correct summary would be that CPU usage would go up because of allocation and copying. Memory, well, it'll also go up because of the fragmentation and allocation overhead. As for cache, it will decrease because the locality due to copying. It changes every batch. So yeah. Question two was why the reference is faster. Reference of array f64 is faster. You answered vague. Array easier to index. Irrelevant. Oh, uh, well, ampersand and then square bracket f64 is faster because it creates a view into existing memory without allocating or copying. Eh, I don't know. Well, the key difference is vector per batch does something like this. So batch is equals to like data and then start to end range and then to vector. So allocation and copying. Whereas slice view is something looks like this and no need to copy, just the reference of it. All right. So core principle is performance, avoid memory movement. Yeah. Lifetime of A. Your answer, it cannot exceed lifetime of A. Partially correct, but not precise enough. Oh. This A ensures that data set structure does not outlive. Yeah, it cannot exceed means it does not outlive the data it references, preventing the dangling reference. Oh, I didn't use the word dangling reference because it never happens in Rust. Rust prevents it. Any ways? Now let's see why this uh, why this matters here. So you are doing something like features and then we are taking the reference of F64 with a lifetime of A. Now this means that dataset does not own data. It borrows the data somewhere from somewhere. Now the Rust guarantees safety at compile time. Now system level connections, which is very important. You just moved from Python conditioning affects convergence to Rust, which is memory layout affects throughput. Now, unified principle is performance bottlenecks comes from structure, not just algorithm. Now we build Rust step by step. So now we build it. Write exactly this. So step one is dataset.rs and write exactly this. And now since it's asking too many questions, I'll say ask in MCQs, ask in MCQ format. And before going anywhere, we'll first of all create this dataset.rs. We'll not copy it. So let's keep that in mind. Let's get out from this Python LL. We'll create this Rust. So, serial Rust. We'll create dataset, isn't it? Dataset.rs. Dataset.rs. And then we'll create a public structure dataset. Public, insert more, public struct data, capital D, yeah, data set, which will have a lifetime because it is borrowing some things, lifetime of A. Then we are defining the data sets which are there, features, targets, and samples and features. All right. Public features, samples, n target, whatnot. Features, target, and samples and features. Oh shit. Oh shit. I had to do everything. dd, and over here, let's go to the second word. Let's insert something. Features. Let's do line by line. Features takes a reference of f64 with a lifetime of a. Lifetime of a takes the reference of f64. So f64 semicolons. No, comma. Did I forget how to define? Yeah, I think I did. Because I've not written this Rust for so many days. Targets. Targets. Yeah, there's S to it. Same type, which is type of a reference with a lifetime of A. Same F64. All right. Targets, features, and samples and features. Public and samples, and then we have public and features with the same type. All right. And samples and n features, which is reference with a lifetime of a u size, I guess. Oh, nothing. Just directly u size. Great. Yeah. So n samples, n features. Then I don't want to answer it, so I'll just say something like ask me in MCQ format. Ask in MCQ format. No, it doesn't. So question one, what should be the answer? No, but there are two no's. So no, it borrows data. No, but Rust will copy automatically. It will copy automatically, or will it? It borrows because we are taking it by reference. But what happens for the U size? Are we also taking those by reference? So let's like take the borrow because that's the safest option, I think. Lifetime safety. So if the original data or the feature targets is dropped, data cell will still work? No. Data set becomes unsafe at runtime. Yeah. Rust compiler will prevent this situation. It tries to. Data will be copied automatically. I think Rust will try preventing us from doing this, but if not, then it'll create some runtime errors, which nobody wants. All right, we always want compile time errors so that we can solve them. We don't never want a runtime error because we can't solve them until it happens. Zero copy reason. So why is this design zero copy? Because slices are faster than vector. Because no memory allocation or copying occurs. Exactly. B option is the right answer. There is no if and but. Now, because Rust optimizes it internally, no. Because F64 is oh no. Now, fourth question, it says, what does reference of F64 actually represents? A dynamically growing array? Yeah, because it doesn't have a length, so I think so. Or is it a pointer plus length view into existing memory? It can be. B, a heap allocation, fixed sized array. It's not fixed size because length is not given. So I think a dynamically grown array, or B. Or I think A. Let's go. Oh, so I actually created the dataset.rs, but it was just there for asking questions. What a foolish person. Well, everything. Oh, shit. Everything was going correctly, and the answer for this is B. Exactly. Not exactly like there was if and buts, but yeah. I didn't knew the answer, and now I got my answer. It is not an array. It is, a pointer and a length, which is like U size. U size is also the same. Uh, it has a pointer and a length, but it is unknown for some time, isn't it? I don't know. So first C, it's correct. Dataset borrows. Second C, correct. Compiler prevents tangling reference. Three B, zero copy, no allocation, no copying. Good. Question four, wrong. So correct answer would be pointer plus length view. Why your answer is wrong? You chose a dynamically growing array. Well, that describes vector, not a slice. All right. So if there is a dynamically growing array, it's vector, not a slice. Whereas this is a slice, which is, what a reference of F64 actually is. A slice is, a pointer to the data and length, just length. So pointer means the reference. As for, are we taking the reference of the whole thing, that is pointer to the data and the length, or something else? It does not allocate memory. Own data grows dynamically. Visual model would be original vector 1, 2, 3, 4, 5. Well, since it's grows, so 1.0, 2.0, and so on. Slice is like increases pointer, length is equals to 3. So slice would look something like 2, 3, 4. Oh. I got it. I got it. So we are actually, first of all, well, declaring a vector. All right. Then we are saying we have a slice of that vector, which is, has a pointer where the slice is starting from, and the length it should go. All right. So let's say if we are slicing the vector from the index 1. So we'll say slice has has a pointer going towards the index 1, which is 2. And then for the 3 length, it will go forward. So 1, 2, and 3. So it will cover up number 2.0, 3.0, and 4.0. So that's slice. So no copying, just a view because of the pointers. And since everything is contiguous, so there's just one pointer and everything gets cached. I think so. Isn't it? It's just there is a one pointer, so it has to go. And after that, for 3 times, it gets whatever the consecutive 3 numbers are. All right. So no copy, just a view with a reference. All right. Now, why this matters? Like if you confuse slice with vectors, I've never used slice, so I actually confuse this with not vector, but array. So yeah, you'll accidentally introduce allocation. So yeah, don't confuse this with vector. Your zero copy pipeline becomes fake. Oh shit, I don't want it to be fake. I want it to be real. So now you are ready. So we move to the core of this exercise. So step 2 is batch without allocation. Your task is implement the data, the no lifetime A for data set A, implement a method batch and without allocation. So we are not allocating anything. We are just taking the reference of the self and we are saying the start of the use size and the size of the use size. And we are returning a type which is batch with a, well, lifetime of A given this structure. So I think what I can do is right now is I'll say vim first of all, I should make it 2.rs and let's save it. Before that, let's move this dataset.rs as 1.rs because it doesn't make much of a sense. If it does, we'll name it properly. All right. If it doesn't, we'll just create it like first, created second, and all that. So what is 2.rs? Let's get into 2.rs. 2.rs, and it says we have given a data set that is batch. So it means that we have a public structure declared that is called batch, and what it has is the lifetime of A, right? And now we implement X, which is usize, and Y, which is usize. So X is of type of usize, if I remember correctly. And then there is a Y, which is again of size usize. I think this is what, no. Like, yeah, it is usize, but in a different andas. So let's change this. First of all, X is there. It's public X, and instead of usize, we have a reference. We'll change this CW. We have a reference ampersand. Then we have a lifetime of A. and then F64, isn't it? Yeah, exactly. So we have a slice. Same for this CB. So we have a reference, we have a lifetime of A, and then we have F64. Exactly. So I think we can now implement the data set for this. So implement a data set for batch of whatever the size is, start size, start. Oh. I think I made a mistake. I made a heavy mistake. Like I should have created a data set.rs. So let's save this. Vim day like data. Yeah, exactly. Data set.rs. Let's save it, isn't it? And we'll copy this. Can we just append whatever we are getting from this directly? Input this to dataset.rs. Will this work? Let's try catting the dataset.rs. It does. Now let's append, you know, 1.rs to dataset.rs. Well, I never did this. Now I did it and it works. So kudos to me. Yeah. Now we have two structures, which is, remove the 1 and 2.rs. This is our structure now. This is our tree. And let's vim into dataset.rs. Now we have structure batch, we have structure dataset, and we want to implement. We have to implement with a lifetime of A. Oh, lifetime of A for dataset, which again has a lifetime of A. What do we have to implement? We have to implement a public method that is called batch for self and self what size and what reference of self first of all, then start and then size. So reference of self, then start start, which is of type something, and then size ze, which is of type something. I think the type is u type or u size. Exactly. So u size, exactly, and a space u size, isn't it? Yeah. So this is exactly what we are getting, and then the return value will be in type of data structure that we defined as batch, batch, with a lifetime of a. Again, everything has a lifetime of a, and that's our implementation. That's it. Now, critical thinking before coding. So answer these MCQs first. So feature layout. If your data set is n samples, which is 100, features is 2, and store as a flat array. Oh, damn. X11, 12, 21, 22, 31, 32. Now each sample occupies what? This is a flat array, so uh, each sample, 100 samples, and we have 200 sort of combinations, 1, 1, 2, and so on. Each sample occupies one element, two element, n samples element, unknown. Oh, well, logical answer would say something like one element. And if there is any exception I don't know about, then please do let me know. Now two, it's hanged even at 85 or 87% utilization. So two, batch size range. So to extract the batch starting at start and u size, the feature slice range is to extract batch starting at start and size with a size, like it's starting from, let's say, index 3 and with a size of, let's say, 4. So it will grab 4 elements starting from the index 3. So feature slice range is features, we have a slice, what's its range? So we are starting from the index start, uh, then we are going, like we are starting from 3 and we want next 3 elements. So we want, including 3, we want 4 5. All right, so 3 4 5. So if we are starting from 3, our size is 3, it means we have a start of 3, we add a size 1, we add 4, we add size 2, we add 3. So yeah, option A is correct. Option A seems correct. And what are these complex features? Well, oh, feature slice. All right. So we are actually storing everything linearly as a flat array. Are we doing that? Why are we doing that? We don't. We shouldn't. Feature slice range is not. It'll change dramatically. So I don't know. Logically, this makes sense. But now, since it's flat array, so this will be wrong. So we'll have to say something like well, I'll go with the simplest one because I can't understand all these stuff for now. We'll answer it A because that's my understanding. If it is wrong, well, it should improve us. So now it says, why no vectors? Why must we not use vectors to vector? It's close syntax. No, it is not. It is like comfortable uh, where it's needed, but it does something like allocation and then copies the data. So we can't do that every time. So B. Safety check. What must you ensure before slicing? And I'll also, oh, did I press enter? If I did, I didn't. Sorry. Why you must ensure the slicing? What must you ensure before slicing? Yeah, safety check. That the start should be greater than size. No, no, no need for that. Or there is. What else? Start plus size should be less than n samples. Should it? I guess so. Because where we start, we we are starting from, let's say, number 3 and we want to go 3 numbers forward, so it should be inclusive in our samples. So yeah, B seems correct. Size should be greater than n features. Let's say we have 3 features, size should be greater than those. No, I don't think so. We can get a size of 1. So I think this is B. As for nothing, I don't know, but let's give it a, well, my code. Here is my code of data set.rs. Nothing of sort of rocket science, but yeah, it is there. So let me remind it that I have something called code of dataset.rs. Press enter, paste it, send it. It's hanged here. It's hanged. What shall I do? 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 It's hanged. You attempted both reasoning and implementation. There are two major conceptual errors and one missing implementation. So it is like you answered A incorrect. Correct answer is B. Why? Because each sample has n feature element given these. So each example would be like I1 to I2, like two elements. So answer is B. Let's see what was the first question. Each sample occupies two elements. All right, not just one, because there is first of all a sample and then features. So each sample occupies uh, two elements because there are two features for each sample. Okay. So that's what it's saying, that each sample has n feature element given. So each samples like ix1 and xi2, so two elements. Answer is B. Correct. Critical correction is a sample is not one element, it is a row of features. All right. I thought sample is equal to n sample. So yeah, I mistaken it. But it was not. Sample is, we are talking about sample, then we are talking about uh, the whole sort of row of that sample with all these features included. So if feature becomes 3 or 4, well, each sample takes 4 elements. All right. And because of that, answer 2 was also incorrect, which was like batch starting slice and ending slice. So yeah, it was incorrect. Why? Because of this critical error. Answer is B. Why? You must skip entire sample, not individual values. Correct slicing would look something like this. Start and then n features, we have multiplied n features. Then this is our starting point. All right. Then we range it from start plus size, which will be our ending point. But then we are again multiplying it with n features. So if there are two features, we must skip by two every time. If there are n features, we skip it by n. So that is our range. So B is the correct one. Now question 3 is correct, 4 is correct. You cannot implement batch correctly until question 1 and 2 are fixed. Now fix your code. So your current code is incomplete. Why is it? Uh, oh. So I didn't implement anything. Yeah. What this does is understand this. Features is like feature start. We have a start and then n features, like how many features are there. That's feature start. Feature end is start plus size, which should be have been ending range, but we multiply it with features so that we can get the whole rows, because data is flattened. Yeah, but why can't we just make a matrix? Or is there no such thing as matrix? Then why can't we make, nah, let's not make arrays. Well, arrays, but vector of vector. So let's not make that. Yes, that will be too cumbersome. And it will not be contiguous. So yeah, speed matters, cache matters. So because data is flattened, our features and end become something like this. Targets is that from start to end, because one target per sample. So sample is all about row. So matrix, a whole row is a sample. Visual mode is if n features equals to 2, the data set is like x1 1 and x1 2. This is a sample 1, this is a sample 2, this is a sample 3, this is a sample 4. So if we arrange it in rows, so x1 1 1 2, then below that we should have x2 2 2, x21 2 2, and then below that we should have x31 3 2, and below that we should have x41 4 2. That's how matrix are well stored. But since it is well flattened instead of being 2D, we have something like this where we have to well multiply it with features or the number of features, isn't it? If it's 2, we have to multiply each element, uh, but whatever the range is with 2. All right, now it says batch. We have a start size of 1 and size of 2. So start from 1, index of 1, I guess, or sample of 1, or index on 1. Like start index starts at index or just a sample. And then we have a size of 2. So samples is like 2 and 3. So we are actually starting from uh, well index 1, not just sample 1, but index 1. And then we move like we need two things. So sample 2 and sample 3. We get two sort of data, and that's our slice. Sample 2 and 3 is what we get. And slice indicates something like this: 2 into 1, 2 into 3, which is 2 to 6. Why 2 is multiplied to the start? The start was 1 because of the features. We have two features. So therefore, this became 2. All right. So instead of getting index 1 and getting confused with this number, because this is index 1, this is index 2 actually. All right. But sample wise, this should be what we start to get, isn't it? Yeah. So this makes sense. And ending is like 3. So we should go till the index of 6. This is our index 6 where we'll finish what we needed and we'll return. So final test. We go before that, let's implement this because now we understand how it works. So let's implement this. All right. So we have implementation for the batch. We'll have a end, which is start plus size. And then we'll assert that end is less than or equal to whatever the sample we have, because yeah, otherwise we'll just go out of bound and we'll cause some memory problems. All right. So we'll first of all check whether end size is well comfortable in our samples, and then we'll start feature start and feature end. We'll multiply that with n features, like number of features there are, and then that is our range. So for the range, for the range, uh, we'll get the whole self dot features and there is a range. And then for targets, that is stored and y, we have a start and end, like the start and end. Why? If we do this, it will be irresponsible for us. Like, why are we doing this? What are we actually trying to achieve from this? Because if we say start and we start from here, like index 1, and we'll gather two steps, which means 1, and we'll go from here to, size was 2, so 3 elements total. No, 2 elements. So 1 is this, 2 is this. We'll just grab these, and that's it, which is so wrong. Why are we doing this? Let's first of all, implement this, and then we'll think about why are we doing this. Let's first of all ask, and then we'll go on with our lives. Why are we doing this range when it is clearly wrong? All right, now let's get to our implementation, which is vim dataset.rs. And in implementation, let's go. So we'll say end is equals to, but end we have to define. So do we define? Yeah. Start and then plus size will become our end. Apostrophe. Apostrophe? No. Semicolons. Let end is equals to start plus size. Exactly. Then we assert. Assert what? That end should be less than equal to a self, isn't it? Self dot n samples. Self dot n samples. It is. Then we'll say batch out of bound. BATCH of BOUND. So if end is, less than or even equal to the n samples, we'd say batch is out of bound. After that, let's do feature start, feature end. We'll say let feature feture should we use s, feature no s, start, and then we should have feature end. Let's do that. PATURE feature end. And what we are actually doing is just multiplying start and end with a self end dot features. All right. So what we are taking is start start start, and then we are multiplying that with self or reference of self, uh, just self. All right. Self dot n features TURES. Then we say start. No, sorry, it is end. So we'll say end, and we are multiplying self dot n features to it. ATURES. Semicolon. Don't forget semicolon. It's important in C and Rust. Semicolon is important. Now we say X and Y. So X is self features and Y is, I don't know, targets. So let store X is equals to, and then we'll store let store Y is equals to, and we are passing a reference of cell dot FEATURES, for the batches. We are taking the reference of self features from the range of feature start to feature end. FEATURE, है ना? START to feature, FEATURE, and end. That's what we are doing, isn't it? And over here, what we are doing is just taking the start and end, not features. So this is targets, and we are saying start to range of end, like a normal person would. But since the data set of a matrix has been flattened out, this will give us a wrong result. So I don't know why we are doing this, and we want to return X and Y. So why are we using semicolons? We can directly say like this, and it must get returned, or we can enclose that in a batch. Exactly, because this is not batch. Let's create a batch. Batch is our data structure which has X and Y value. right? So we'll create a BATCH batch, and inside that we'll pass X comma Y, and this will be returned. Exactly. So I think now we'll copy this. We ask the question and then we paste our real code. And I think we'll move on. But before that, let this browser stop hanging so much. And we have few questions, so let's answer them first of all. One, let's answer this one. So it says we have not 11 but 1. So it asks me that if we have features 3 and we are starting out from 2 and till the size of 4, what should be our range? So 2 multiplied by 3 is 6, 4 multiplied by 3 is 12. So 6 to, no, 4 3s are 18. Sorry, no, 4 3s are 12. Shit, my maths, my maths. So instead, I am just directly getting the option C. No need for maths. Yeah, 4 3s are 12 and 2 3s are 6. So this is 6 to 12. All right. This 18 was there so that we could get confused and directly press that. Now it asks why do target not use n feature multiplier? I don't know. I don't. That's my question, isn't it? I don't know. Why do we even have target? If you mistakenly do something like this, what happens? Work finds? No. Wrong data alignment. Exactly. So no panic, no compiler error. It's just something that we didn't want. We want our right data, not a wrong data. And so all of these, and we'll move to benchmark. Well, we want to benchmark it. And we did not started a project using Cargo new, so it's just a dataset.rs for now. But we'll do that if needed. Good, you're questioning the right things. So let's resolve this precisely. The confusion, why is, why start to end correct? Uh, well, you think it's wrong because you're mixing feature layout with target layout, and I don't get what the both of them are. Like features is something, yeah, we need them because we are calculating based on it, but why target? Core distinction is you must lock in this. So feature X is like shape conceptually, where we have n samples and n features stored as a flat. So we have this. So each sample is a multiple value. So we need to start from start multiplied by n features. Target Y, which is shaped like this, n samples. So we directly have y1, y2, y3, y4, y. So each sample is equal to one value. Oh, so target is different. Target is different from others because we have. So feature is flattened, target is not. What is target? Nobody knows, but we have some target. And since it's not implemented properly, we don't know actually. But it says target is something like normal ensamples. No ensamples and n features like a matrix, just ensamples. All right. Oh, targets is y. Oh, so features, feature was our matrix which was x, and then target is our y. Oh, all right. Like compare that to Python one. All right, this. I don't need to reconnect it, but think about this. This is our x. So x is a matrix. Well, a 10,000 by 2 matrix over here. So if it gets flattened out, it'll have a 20,000 elements. But whereas y is just a single row, multiple columns element. So just single thing, which is like one row. So 1 comma 3. Sorry, 1 comma 3 or 1 multiplied by 3. So if it gets flattened out, we'll still have a 3 elements. So nothing to worry about because it's already flattened out. All right. So I get it now. That targets is y, whereas features is x or x matrix flattened out. Therefore, features slice is looks something like this, whereas target slice looks something like start to end. Visual example would be like let n features is equals to 2. So we'll the features we'll take something like this, but targets we'll have something like this. So this is a sample 1, this is a sample 2, this is a sample 3, this is a sample 4, like matrix flattened out, whereas we have 2 features for each of them, isn't it? And 3 4 4n, not 10,000 but just 4n as for n samples. N samples are 4 and n features is 2, so therefore we have 8 elements right over here. Whereas target, we directly have y1, y2, y3, y4. Exactly. So batch is like starts from 1, size 2. You want a sample 2 and 3. So features would go something like 2 to 6 instead. Isn't it? And targets would just go to 1, 2, 3. Not, grab the third element because it's not equal to, but just give it a range of 3. Your key mistake is you assume target also needs feature style indexing. Wrong, because target are 1D aligned per samples. Yeah. MCQ evaluation, you answered C incorrect. Correct would be B. Why? Because n features is 3, start is 2, size is 4, to end is 6. Feature slice is 2 multiplied by 3. Oh, what the heck? Oh, shit. End is start plus size, which is 6, and then multiplied that by 3. So 6 to 18. Exactly. Shit. So I was confused earlier. Now I am not. So question 2, you said I don't know. Now you do. Targets don't use n features because each sample has exactly one target. Exactly. Now question 3 is correct because wrong alignment. There's a silent bug, worst kind. Well, which one? Let me see what the question number 3 is or was. So this one, n features. Yeah, this is the worst bug because there is no Rust error because there is nothing wrong with our Rust program, but the data set that we are getting would be wrong. So yeah, it's a silent bug and a worst kind because every silent bug makes you count. Why targets exists? Important. You asked why do we even have targets? Answer, you're modeling y is equals to x w plus noise. Exactly. So x should equal to input features, y should equal to ground truth output. In training, prediction would become something like x matrix multiplied by w's, and errors would become something like prediction minus y. So gradient depends on this error. Without y, no learning signal, no loss, no gradient. Exactly. Now system insight. You just implemented a zero copy mini batch loader. A little bit, yeah. This is what exactly real ML systems do under the hood. A final step, benchmark. Why now we measure why this matters because we'll create a benchmark.rs. You will compare copy version, that is this, slice version, that is this. We'll compare Slice version, not the copy version. Okay. Benchmark template looks something like this. So this is a benchmark template. All right. Now I think we'll have to create a cargo. So let's create the cargo. We are creating data sets first of all, and second of all, we are benchmarking it. Which one is sort of good structure? So to do that, we'll name it cargo new, and we'll name it dataset. Da set, isn't it? Oh, so let's first of all remove this because it is not snake case or kebab case. It should be like data set directly. Data set. Now this is snake case, isn't it? It is not. Snake is like normal. RF instead of data. Yeah, capital S. Do we have to, does it matter? Well, it doesn't, but we are still trying to do everything the best we can. Hmm. Let's treat so that we can see what is there. So there's main.rs. So we'll create that as well benchmark.rs instead, isn't it? Because it doesn't say like, yeah, it says benchmark.rs. So we'll do that. I think we'll keep that main.rs for now. And let's move this dataset.rs to our rs to our dataset source. Let's treat now. Yeah, our dataset is over here. Let's vim into dataset and then source and then benchmark.rs, benchmark, benchmark, or ba, what is this spelling? mark, bench mark. Exactly, benchmark.rs. Now, now benchmark template looks something like this. We'll have a use standard time instant. Says use, oh, first of all, insert mode and use what? Standard time instant, INSTANT. I guess this is correct. Time instant. And then we'll say public function benchmark. Then we'll create a benchmark function. Where do we call it? We'll have to call this in main function, I guess. And we have not imported yet the dataset.rs. So, well, let's do that too. Public function, benchmark, benchmark. Oh, benchmark, and then features, and the feature is of type reference of F64 features, F64 n samples, use size, n features is use size, n patures is use size. Since it's our first time, I think we can copy and paste, not like type it out one by one, not copy and paste, so that we can understand it more properly. And let's move on. Mhm. Now we have batch size and iteration. So let BATCH size is equals to 10,000 and let ITERA3ION iteration is equals to how much iteration? Oh shit. Iteration is 10,000 and batch size is just 32. CW, not like this. Let's write that. 32. Uh, we have iteration and batch size. Now copy version. So we have two versions because we are benchmarking both of them. And which one would be faster? That's what we are doing. I think for the day 9. So we are saying let's start is equals to instant now. So we are starting the time watch or whatever this is. Instant, and then now like this or like what? Instant now. Yeah, exactly like this. Just two colons, not just single one. Oh, I think the keyboard is misplaced, so something is happening. We have start and then for I in 0 to iterations. So we say for I in 0 to iterations, which is 1,000 times iteration, not iterations. I think here the variable name was also iterations. So yeah, it made sense. Iterations. Let's change it if we want to. Yes, it will not be a problem because of this S, but it might be because sometimes I might write iteration, sometimes I might write iterations, and that will be a problem. Now index S and E. So index is right. Let's first do that. Let IDX, let S, and let E. So our index is equals to I, then n samples minus batch size. So I in a bracket. Yeah. We have I is this percentage, and then n samples, say MPLES, and batch size minus batch size SIZD. This is index. S is index into n features. S is like starting. All right. S is equals oh S is equals to S is equals to index into n features, isn't it? FTURES, n features. Ending is, well, it is starting S plus the step. So instead we write index plus batch size directly, and then that multiplied with n features. Exactly. INTX plus batch size SIZD. Oh, not these brackets, just normal circled ones. Index plus n feature, index minus plus batch size multiplied with n features, multiplied by n features, n features. Is it incorrect? I don't think so. Is it correct? I hope so. So this is our, well, copy version. Now let batch is features s2e, and then this is the copy version because we have two vector. So we are creating a vector out of it. Over here, we are not creating a vector out of it. So same, exactly the same, just this syntax changed. The rest, everything is exactly copy and cut. Copy and paste, actually. All right, so let's make this last line. Since it's unused variable, therefore we are saying let, unused batch is equals to batch, batch is equals to features, features, and we are indexing from S to E, and then we are copying it. So we create using two vector method, and now this will be created as a copied vector. Let copy time. All right, so over here we will say let copy time, isn't it? Copy time, py time, and the time is up. So we'll say start is equals to elapsed. Start dot elapsed, and this is a method. So elapsed, oh, elapsed, yeah, elapsed. Start dot elapsed. I think this is done. This was our implementation. Now we have a slice version, like exactly the same. Just the two vector was gayab. So we'll copy the 9 lines. So yank 9 case and 9j. Let's paste it on the new line. It got pasted. Now this is not a copy version, so we'll say instead of copy version, it is what? Sliced, isn't it? It's a slice version. Right? We have a start, we have not copy time, but slice time, isn't it? We have slice time. SLICE, slice time, and start elapsed. And instead of converting it to vector, we are not doing anything. So we'll say C3W, a semicolon should be there. It's good enough. And we'll just now print it. We'll say vector allocation time, and then let's not take this semicolon. Let's say print ln, since this is a macro, and then we'll have something like vector allocation time, isn't it? Vector allocation time, and then whatever the time is in a default mode, sorry, not default, but debug mode, and then the copy time, copy time, copy time, print ln slice view time, SLICE, VIEW time is this, which is in again debug mode, and then we have what? Slice time. There is still an error. You know what it is? We have not imported the dataset.rs. Do we have to import it right here? I don't think so. Or I should think yes, we should. We should import it. But let's not do it unnecessarily. We want to see the errors we can get out of this. We have to say cargo run and it will run. That's how easy it is. Before that, let's answer it. So final question, answer before running, which like, uh, why does two vector slow things down? And why is, so question one, again, it slows things down because of uh, copy and allocation of a vector. We see DOR. All right. Two. What is two? Why is slice version almost constant time? We, oh shit. We do not create any other vector by allocation and copy. We just use pointer and the start pointer and the range and the range. That's it. Three. What kind of bottleneck is this solving? Compute memory. Yeah, obviously memory bandwidth, because copying an allocation, well, it takes lots of memory. So memory or bandwidth error, not compiler, not syntax, not anything else. Submit of run benchmark. Well, how should I? If I say cargo run, it will probably give me an error. If I say, well, first of all, cd into this dataset, and if I say cargo and run, it gives me an error. Oh, sorry. It did have a main.rs, so that's why everything worked out. Well, how about just remove this source main.rs? Now what? Cargo run. Yeah, failed to parse cargo tomls cost, no target, well, either source is library, source is main. rm-rf, then we'll target the target. Oh, not temp, sorry. Target. Now, if I say tree, it'll probably give me a tree. And if I say cargo run, it'll probably give me an error. But let's try doing this. Will it work? I don't know, but let's try. Rust C and give it a file called benchmark.rs. So first of all, there are many errors. Let's solve them one by one. So it says instead of this, you can do this. No problem at all. Unnecessary parenthesis. And this is just a warning. All right. This is not an error. This is not an error. This is. So main function not found in create benchmark. Exactly. So it cannot work. Either create a main function or just use main.rs. So we have to use main.rs. And then there's a bigger function, like doesn't have a size nor a compile time. That batch is, let's see, if batch was a reference. No, it was not. So I think my code is correct, but consider borrowing here, but that will also not help us. So the main thing is we have to create main.rs, but what will we actually implement? Nobody knows. Cat everything and then wl copy it. paste it, go back, let's do the tree. Let's go back first of all, and then do the tree, and then we shall say, we shall not say anything. Just paste it and move on with our lives. Your answers are correct. Implementation is almost production level. Now you finalize and tighten the gap. Good review, important fixes. First of all, slice benchmark is slightly misleading. This is not a slice reference. It actually tries to copy. So this was actually an error, not just a, well, even compiler suggested it. So let's do that. Get into SRC, get into benchmark, where we have a features. Let's get to the word. Let's insert a word that is 10%. Same over here. Save it. Issue 2, compiler optimization risks. So Rust may try to optimize away the unused variable. Your batch is unused, so it may become invalid. So we'll try doing this. Let me see. So everything is same now. Oh, no. For slice version, there is. For copy version, there is not. Oh, damn it. So this was my error. It says in line 25. So if I go to line 25, yeah, here we wanted to add this ampersand, not here. So let's undo this. Let's go to the word. Let's cut it out. Vector version, use this. Missing target benchmark option. Optional but better. Right now you're benchmarking only features. That's fine, but note that real pipeline, since both X and Y, so final correctness would be like this. Instant and then black blocks. How about we copy and paste it? Because there are just few, let's not do that. Let's not do that. First of all, do not say this is an unused variable. First of all, do not say this is just an unused variable. So wherever this is found with a batch. Oh, escape this. So yeah, this is found. Nothing. So it says over here, remove this, and in a new line, we shall say something like black box, LACK box, and then pass bash to it. BATCH bash to it. Right. And then let's copy this. Let's paste it over here. And then what? Let's create this. Yeah. And at the top, we have to also say use. Oh shit. What did I do? I was not watching it, but yeah, let's go to this and let's open up a line. You'll say use what? Standard hint black box. A standard hint and then BLACK a box. Exactly like this. And then a semicolon to it. I think everything is correct. And features to vector, reference, pop and features, no vectors, price time and all that. System insight, very important. You just implemented Python side of conditioning control, Rust side memories, layout, control throughput, and unified principle, efficient, good plus math. Good math plus good memory behavior. Final check is concept plugin. Oh, before that. How to run it? Should I just say cargo run or use Rust C? Why didn't we imported the data set .rs into the benchmark? And lastly, what should be written in main.rs if we are uh, using what? Well, Rust C. Sorry, if we are using cargo run. Correct answer is, well, use cargo run, not Rust C. We have main.rs, dataset.rs, benchmark.rs, this multi-module create, Rust C for single file compilation, not a project. Cargo run does this. Why didn't we import dataset.rs? Because you didn't use it yet. Your benchmark uses this, not dataset. All right. When would you import it? If you do something like that dataset is equals to dataset and then type dataset.batch. What should main.rs contain? This is a missing piece. Minimal main.rs would look something like this. We have module dataset, we have module benchmark, use benchmark. Oh, so we have defined benchmark. All right. This is function benchmark. All right. So that therefore benchmark, and then we are declaring the n samples, which is 10,000, n features, which is 2, but we have also declared it over here. No, this is iteration. All right. Create a dummy data, and that's it. Okay, let's write main.rs for now. Let's save it. Was there any error? Was there any error? I don't see any red. So let's, vim src into main.rs. Let's write it down. Well, declare the module bench mark benchmark. We have module dataset, isn't it? No, dataset. Okay. Then it says use benchmark. So we are using benchmark benchmark double colons. Exactly. BNC, because that's the function inside benchmark. So benchmark benchmark. and then we create a function main. So function main, and then we do what? Then we create or implement the function main, which is well, let n samples samples is equals to 10,000. That's it. Then we create features. So let n features features is equals to what? Is equals to 2. Then we have create a dummy data. All right. Create 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 a dummy data. Then we are creating it. So let mutable features. Let mutable features featu features features. Let mutable features is vector, and then with capacity. So with CAPA by capacity n samples multiplied with n features. And for I in range of 0 to whatever the n samples multiplied by n features is, like the whole flat data set, we are doing what? We are doing features dot push I as f64. Let's do that. For I in range of 0 to whatever the n features and samples multiplied with n features are, TURES. What we are doing is, first of all, does it need semicolon? Nah, it needs curly brackets. This is not Python, this is Rust, baby. So we say features not push, features not push, and we push what? We push I, but as f64. So we are converting I, whatever the I is, as f64 because that's what features takes. And then a semicolon. And finally, we are returning what? We are returning benchmark, benchmark, and we are passing what? We are passing the reference of features, and what it takes is sample data, samples and features. So you're passing the n samples and samples as a reference of n samples, isn't it? And then n features, n features. We cannot do in any order, so please, that will ruin the whole thing. A semicolon at the end, and it's done. And if we say cargo run, it should run cargo and run. Damn. So these were our warnings. Why? Because batch is never used, so unused. Similarly to these, and well, let's remove these brackets. All right, this parentheses on line 23 and 11. Let's do that. Line 11, not 111, but 11. And let's go to the word exit. Let's go to the end. Where is the end? Exit. Line 22. Below that, let's go to the end. Let's remove this. Let's go to the here. Remove this. Everything works fine. Do cargo run. A bit less of error. So batch, no problem at all. It says dataset has been, unused. Doesn't matter. But at times, so times have changed. This was 1 millisecond, uh, and 330, whatever this is. So I ran it 2 times. This is my first result. Let me copy the second one. So this is my second result, which is very close, but still, it's literally doubled in the first case. It's I hate this computer hanging. It has nearly doubled. Let's do it as well last time. Let's run it. And now this is consistent. Let's do again. We want something different. Yeah, now this is different. And we can copy it. Let's say new line, enter, paste it. I think this is our day 9. I think it'll end it now. It has been nearly 6 hours. So yeah, this video will not be of 6 hours because I'll cut few silences and breaks. Good. So it says you executed correctly, you and got a meaningful number. Now we analyze like a system engineer, not just an observer. So benchmark result says something like that. Oh, this is, oh, so this is microsecond and this is millisecond and this is microsecond. All right. So that's, oh shit. I just got confused for a bit. But this is the vector which is taking 1.28 microseconds, whereas slice is taking 0.38 microseconds. Like not even third. It's like, I don't know, 38 with 2 times, 3 times, 4 times, 5 times, like nearly 5 times lower than vectors. Similarly, over here also, nearly 5 times lower in slices. Vector is nearly 5 times, takes more time. Similar, like 59 and 60, like same. And 2.25, 2.50, same. Yeah, 5 times. Step 1 is compute speed up. You must always do this. Take average roughly. So vector, yeah, it is 4 times over here, but yeah, nearly 5 times. All right. Interpretation is slice based batching is 3 to 5 times faster than allocation based batching. Yeah, exactly. Step 2, why this gap exists? Precise. Vector version does not allocate, sorry, vector version does this. What? It does allocate and copy and then deallocates, whereas the slice version does not. It just points towards existing vector because that's how it works. So cost component is that allocator overhead is there in vector version. Memory copy happens for O batch size into n features. So this is O log n. So yeah, cache disruptions is there. No, it is not O log n, it is O n. And whereas n is the size of, the flattened out array, flattened out matrix, which is stored as an array. All right. So if it is a matrix of 10,000 multiplied by 2, which is, 10,000 by 2, we'll have a 20,000 elements. So O of 20,000 is our complexity. So memory copy will take that much time. Cache is disrupted. Slice version does what? It takes a pointer and a length, and that's it. It has a O of 1 every time, which is a constant. So no allocation, no copy, no movement. Best. Step 3, why result vary per run? You saw something like 1.28, then 2.36. Causes could be CPU scheduling, which is, well, damn too much right now. It is nearly touching 80 and 85. CPU scheduling, other processes interference, and cache warm up. So first one often faster or slower depending on the state. Allocator behavior, heap fragmentation varies. All right. Now step 4, system level insight, which is critical. You just demonstrated that Python side has a bad conditioning, so slower convergence. Rust side has bad memory handling that can cause the slow data pipeline. Combined insight is that training speed is equals to optimization efficiency plus data pipeline efficiency. Even if GD is perfect, slow batching is, you know, bottleneck will remains in slow batching. So final concept check: why does slice time scale better as uh, data set size increases? Second is, if batch size is equals to 1024 instead of 32, what happens to the vector time? Well, vector time increases because now it has to allocate 1024 sort of batch sizes, whereas for slice time, it doesn't. It remains constant, which is far more dangerous in production level. Slight lower optimizer, inefficient data pipeline. This one. After this, all right. So this is our end. Let's answer these. Why does slice times scale better as dataset increases? Simple. No allocation and copying and deallocation. It has a constant com complexity of big O of one. Two. It says if batch size were to increase to 1024 instead of 32, what happens to vector time? 2 is like vector will take more time as the batch size has increased. The slice time remains nearly the same. All right, let's move to the third question, which is what? Which is more dangerous? I think the B is more dangerous. So let's just read this answer and we'll end this recording. And I'll start uploading it. Good. Now you are thinking at a system level, but we refine the precision one last time before closing day 9. Evaluation is like it says slice scaling. So you said O to 1, no allocation, correct? Good mental model. Refined version would look like something like this. So slice creation is like complexity of O, big O to the 1, because it only creates a pointer plus length view independent of batch size. Now question 2 is well, batch size effect. You said vector increases, slice same, direction correct, need precision, because the vector, which is well, this is its scaling model, so batch size will get multiplied, which will affect its O size, whereas slice remains the same, which is this complexity of O to the 1. So important ones is that slice time is not exactly constant due to the bound checks, etc., but it's effectively constant related to the copy cost. Okay, so you're not copying, that's why it's constant. It's not constant due to the bound checks, etc. All right. System risk is, you said B pipeline, correct? Precise reasoning would be, you must internalize this, that data pipelines inefficiency affects every epoch and every batch, making it multiplicative. So bottleneck across the each training process. There's just a inefficient, uh, what was that? Inefficient optimization. Yeah, inefficient optimization remains just slightly slower optimizer. Yeah. Well, this will just remain for the language itself, which will correct itself. All right. So I think this is done. Bye bye.